Welcome to BYJU'S exam prep. Welcome to the marathon session. I am MN Ramesh. Welcome to the session on electronic devices. So today we are going to deal with electronic devices exclusively for electronic students and instrumentation students. If you want to score on electronic devices, some questions may be there in GATE 2023 as well. So this is another very basic and very important subject, because this is like building block subject where many subjects linked with this subject. If you want to study some other subjects and if you want to use some devices there like diode, transistor, MOSFET, field effect transistor, etc., special diode, Zener diode, etc., these are all the diodes or devices you keep talking about in different subjects as well. But how they function, how the operation, how their characteristics, all those details will be discussed thoroughly in this subject. So hope this is going to be really helpful for you, and once again welcome you all guys for the marathon session for scoring better and to revise very quickly of this subject to crack 2023 GATE exam. So I request all the students, guys, please share this to all the students as usual. Like from last few days we have been teaching you marathon sessions of different subjects. So today it is the turn for electronic devices. So please share this to all other students to join the session. Exactly at 4 o'clock we started, and going to be 4 hours continuously on this session, and I am going to teach semiconductor basics, and then Sanjay Reddy sir is going to join with us with PN junction and other topics. Come on guys, good evening everyone, good evening, good afternoon. Come on guys, please keep sharing it to other students as well. Let's start this session. Before I start the session, let me introduce myself. As you all know, my name is MN Ramesh, and having experience more than 20 years, done my masters from Osmania University, Hyderabad, and trained across 25 cities in Pan India. Over 1 lakh students, online and offline together. My favorite subjects are analog circuits and electronic devices, and this is a subject now we are going to deal with. Right guys, so let's start with this. Before starting the topic, and not going much details about marathon session and all, because you are already aware of this. We have been doing this session. And one announcement I want to do, that these marathon sessions are for 12 days we are going to complete everything. So this is very important at this point of time. Last 1 month or last 20 days, you just need to quickly revise whatever you have studied for 3 months, 6 months, 8 months, 12 months, whatever. You just need to quickly revise. So we are not going to waste your time, and fastly we are revising and recollecting all the things required for cracking the GATE exam. So that's what this marathon session is. So all branches, computer science, electrical, electronics, instrumentation, all the faculty are going to take the sessions on this. You can see the panel of faculty here. And another very important notification for you or information for you is, there is a workshop going to happen on 10th January, that is day after tomorrow, on how to crack GATE 2024 while you are going to college or while you are doing a job as well. So how can you crack the GATE examination when you are going to college, balancing both college as well as preparation, balancing your job as well as preparation. So you can get the information from Dheeraj Sardana sir, who himself is a ranker and a faculty who can guide you better to manage both. That is really helpful for all the students who are in college or completed working in engineering. Right, now let's enter into the topic. Today's topic is, to start with, is semiconductor physics, the basics of semiconductors. It is another very important topic. Every year from semiconductors there is going to be one question damn sure in the GATE examination. Damn sure. Compulsory there will be 1 or 2 questions from semiconductors every year in the GATE examination. So let me revise quickly in next 2 hours how these semiconductors, why these semiconductors, what are all to be learned in these semiconductors, like Fermi level, drift current, diffusion current, current density, all these things. Let's learn about this. Navneet, good afternoon. Sonali, good afternoon, and inform all other students, guys. Let's go with these semiconductors first, and then we can revise rest of the topics also, like PN junction formation, how PN junction is, forward bias, reverse bias, BJT, MOS field effect transistor, MOS capacitor, special diodes. All these devices are thoroughly explained in a very quick time. That's what revision session is. Are you ready, guys? Are you ready to learn this session? To start with, just to remind you, just to recollect the standards or the constant, the regularly used constants in semiconductors generally or in electronic devices generally are this. So you have to be aware of these constants. You have to by heart this if you are proceeding with electronic devices or you want to score good in electronic devices. Brahmendra Reddy, good afternoon. Satya Shri, good afternoon, guys. Welcome to the session. Please inform all other students in social media groups. You have WhatsApp, Telegram, Facebook, Insta, etc., whatever other Telegram groups. Yeah, charge of an electron is known to you already, 1.6 into 10 power minus 9. Quickly, I will revise so that I can jump into the topics. Mass of an electron is 9.1 into 10 power minus 13. Permeability of free space, mu naught, is 4 into 10 power minus 7. Permittivity of free space is 8.854 into 10 power minus 14 or 8.854 into 10 power minus 12 farad per meter. This is farad per centimeter. So, as per the data given, we have to use. And Planck's constant is 6.625 into 10 power minus 34 or 4.135 into 10 power minus 15 electron volts second. Okay, joule second it is. It is in joules and this is in electron volts. Mostly we prefer this value. So we generally prefer to use in electron volts because the energy of electron volts is expressed mostly in electron volts. So we prefer this. And the thermal voltage Vt, we know all of you this, kT by Q, it is 0.259 volts it is at room temperature. This is at room temperature, it's already given here. So these are the standard constants you must be knowing. Just I am revising, but remember, you have to remember all these values. Okay. Now I am seeing good number. Come on, guys, keep informing other students also. Just a click away, share. There is a share option. Please like the session so that why we are asking to like the session. Because this is the efforts we are putting from our side. What for? To gain very good rank in the gate examination. Who is going to gain the good rank? Not we. You are going to get the good rank. So to reach to the maximum number of students, please like it or share it to other students so that every student will get benefited, because our efforts should reach to maximum number of students. Those who are interested to follow us, to prepare and gain something from us, ultimately they are going to get benefited, not we. Okay, so that's the reason we ask. So it is just free of cost for you guys. Sharing, clicking, liking is not any cost. So just do this. So this helps other students also knowing about the session. Okay. Next, moving on to some other important standards, constants for the frequently used semiconductors. Okay. Silicon, germanium, gallium arsenide are the frequently used semiconductors, and we need to know some constants related to the semiconductors as well. So number of atoms per centimeter cube in silicon will be 5 into 10 power 22. In gallium arsenide 4.42 into 10 power 22. In germanium also 4.42 into 10 power 22. How many atoms per centimeter cube? Like for a centimeter cubic size of semiconductor, in silicon 5 into 10 power 22 atoms. Remember how big this number is, right? Kranti, yes, exactly. Like is equal to motivation. Yes, like is equal to help. Like is equal to, you know, informing the students. So this is all for students, guys. So this is a very important number and surprising, right? How many atoms are there in a semiconductor? 10 power 22. Imagine how big number it is. After 1 there are 22 zeros, into 5 it is. So those many atoms will be there of a size of small silicon. So that is the beauty of semiconductors to start with. Dielectric constant epsilon r, we call it epsilon r, right? 11.7 for silicon, 13.1 for gallium arsenide, 16 for germanium. Energy gap, band gap energy or energy gap, we call it as Eg. For silicon it is 1.12, gallium arsenide is 1.4 and germanium 0.74. Electron density of states in conduction band, NC. NC we call it as density of states in conduction band is 2.8 into 10 power 19, 4.7 into 10 power 17, 1.04 into 10 power 19. This tabular form, you just take the screenshot and save it, and if possible take the printout and paste it in front of your wall somewhere, so that every day you will see this. And NV, similar to NC, density of states in valence band is 1.04 10 power minus 19, 10 power 19 in silicon, 7 into 10 power 18, 6 into 10 power 18 for gallium arsenide and germanium. Intrinsic carrier density, it is Ni, we call it as 1.5 into 10 power 10. Very frequently we use this value. 1.8 into 10 power 6, 2.4 into 10 power 13 for gallium arsenide and germanium. So please make a note of these all values, because frequently we are using. So every time you should not look for the data. If data is given, we can make use. If it is not given also, we can assume these details. Okay. Mobility of electrons 1350, 8500, 3900. Mobility of holes 480, 400 and 1900. So observe here, mobility of holes in gallium arsenide is very high, very high compared to silicon. And if you see, mobility of electrons in silicon is 1350, but germanium is 3900. So it is much higher than silicon. So this is one of the reasons why germanium is used. You may be having a question, when silicon is there, why germanium? Or when germanium is there, why silicon? So every material has its own properties and has its own applications as per requirement. So sometimes as per the requirement we may go for silicon, sometimes we may go for germanium, or sometimes we may go for gallium arsenide. So will they not give these values in exams? Sometimes may not, Raviteja. Sometimes may not, sometimes may be given. If the data is given, you must use the data given. If it is not given, we can take this data from this tabular form. Suppose energy gap for silicon, it is not given, for example, then you can take it as 1.12. If it is given as 1 electron volts, you have to take it as 1 electron volt. Okay, as per that. So this is the standard data, as you all know, you must know otherwise. Moving on to the next one is a big question. There are different materials available. So in my hand there is a material made with plastic, right? It is coming under insulator. So conductors we have, insulators we have, semiconductors we have. Why only semiconductor? Why we need semiconductor? Semiconductor has its own advantages. Semiconductor having its speciality. What are the specialities of semiconductor? Conductivity, controlled conductivity. This word is very important. All of you remember. The devices what we talk in this subject, electronic devices. What are the devices we talk about? Maybe diode, maybe transistor. In transistor again different types of transistors, BJT, FET, MOS FET, etc. UJT. These are all devices, right? But all these devices, diode, BJT, FET, MOS FET, all these devices are fabricated with semiconductors. That semiconductor can be silicon, germanium or whatever, but it is semiconductor. Why semiconductor? Because semiconductor is having excellent property where conductors and insulators doesn't have, is controlled conductivity, whose conductivity can be controlled. We can decide the conductivity. That is the beauty of semiconductors. That is why we want to go for semiconductors. Okay, low power consumption, smaller size is also possible using the semiconductors, etc. are the other reasons, but the primary reason to go with semiconductors to fabricate these devices is conductivity, controlled conductivity. Okay, I'll show you how it is possible to control. The next one is the classification. As I just told you, any solid state material if you take can be classified into 3 types: insulator, conductor and semiconductor. Okay, so what is insulator? You all know. Come on guys, give me some examples of insulator. Insulator is a material which doesn't allow the current to pass through it, isn't it? That is what insulator is. What is a conductor? Reciprocal to the insulator, the material which allows the current to pass through it. Insulator conductivity is almost 0. Conductor conductivity is almost infinite. Highest conductivity, ideally infinite, practically Finite, of course, largest conductivity is possible. Insulators conductivity ideally 0, but practically lowest in the order of 10 power negatives. Yeah guys, come on, give me the examples of insulators. Many examples you know. Wood, plastic, glass, very good. Paper, ceramic, these are all very good examples of insulators. Similarly, can you give me the examples of conductors? What are the examples of conductors? Come on, copper, aluminum, yes, all metals can be classified as conductors. All metals are good conductors. But remember one important point, that conductors, all metals are conductors, that's fine, but different conductors will have different conductivity. Sigma, conductivity means what? Can anybody define what is conductivity by the time? The conductivity of copper is different, conductivity of aluminum is different, conductivity of gold is different, conductivity of iron is different. Different conductors will have different conductivity and which we cannot change. It is fixed already. Whereas if you go for semiconductors, the conductivity of the semiconductors can be controlled, can be decided by us. Based on some methods are there. We can decide what is the conductivity. That is why semiconductors are special for us and important for us. Yes, Brahmananda Reddy. All metals. Okay. So semiconductor is very important for us. The material which behaves as insulator or conductor based on the different conditions is called as semiconductor. Semiconductor means it may behave like an insulator, it may behave like conductor. In conductor also it can have different conductivity at different requirements. We can have that. Suppose if I have aluminum as a conductor whose conductivity is fixed. If I want more conductivity than aluminum, I have to change the material. I have to go for some other material, copper maybe. But whereas in semiconductors, if I have a material, semiconductor with conductivity, let's say X, and if I want the conductivity to be changed to Y, I can modify the same semiconductor to get the conductivity as Y. That is the beauty. Okay? Done? So, its conductivity lies between, remember the conductivity lies between 10 power minus 6 to 10 power 4 ohm centimeter inverse. So, very low conductivity, this is very low conductivity, almost like insulator, to 10 power 4 is very large. Conductivity can be in between these two. That is the beauty of semiconductors. That is the reason why semiconductor is. Now, important classification of this. See, any solid state material you see, any solid state material comes under any one of these three classifications: insulator, conductor, or semiconductor. Take any examples. For example, there is a bottle in front of me. It is made with plastic, so it is insulator. So keys, my car keys here. So this is metal. So it is conductor. So if I say my mobile, okay, inside this mobile there is a chip, processor made with semiconductor. So any material you take, my jacket comes under insulator. So my laptop comes under conductor. Laptop case, conductor comes under conductor. So similar to that, different materials, right? Different material. This glasses comes under any material around you. Any material around you, check it. It comes under either conductor, insulator, or semiconductor. But our interest and our focus is on semiconductors. Okay. So these materials can also be classified based on their energy gaps also. Very, very important, guys. Not only based on the conductivity or electrical properties, the materials can also be classified based on their energy gaps. It is very, very important to talk about energy gaps or energy levels of a material, especially for semiconductors. That is what we call it as band model. So we keep talking about that. So the insulator is a material whose band gap is very large. Band gap is nothing but the gap between the conduction band and the valence band. So this is what we call it as valence band. I will tell you later what is valence band. This is called conduction band. The lowest energy of conduction band is called as EC, denoted here as EC. The highest energy of EV, the highest energy of valence band is denoted as EV, and the gap between these two, that is nothing but EC minus EV, is called as EG. It is called as energy gap or band gap. And if it is more than 6 electron volts, it is called as insulator. if the band gap is small like this, like EC is this lowest energy of conduction band, EV is this highest energy of valence band. If the gap is close to 1 electron volts, close to 1 electron volt, then that material is called as semiconductor. If there is no gap at all, see the conduction band is up to this, valence band is up to this, they are overlapping here. This is the area they are overlapping. This is the region where they are overlapping. Such materials are called as conductors. So these are semiconductors. So we are interested in this. Very, very important is semiconductor whose energy gap is close to 1 electron volt. This energy gap 1 electron volt makes the difference actually, makes this semiconductor something special. Since that semiconductor is having the energy gap equal to 1 electron volts, close to 1 electron volts. I have shown in the tabular form also that silicon is having 1.12, germanium is having 0.7, gallium arsenide is having 1.42, close to 1 it is around, right? So that's why they are called semiconductors, right? So this is also important because going forward in the initial stages, it looks easy to talk about the electrons and holes and the covalent bonds. But as we progress deep into the subject, dealing with the covalent bonds, electrons, holes always is not that convenient. That's why we go with energy band diagrams that gives you more clarity and more understanding about the semiconductor and the devices. That's why we always correlate with energy band diagrams. Okay, that is the beginning of energy band diagrams. Move on to the basic atomic structure. How to understand how semiconductor actually formed, it is better to understand the atomic structure. As you all know, how atom will have a nucleus. Around the nucleus electrons are revolving. Nucleus will contain protons and neutrons. Electrons with negative charge revolve around the nucleus at a certain energy levels. They are called orbitals. All such basic theory is known to you, right? But my here interest is, these are different elements are there like boron, carbon, nitrogen, aluminum, gallium, silicon. We are interested in this fourth group elements in the periodic table. So why fourth group? Because all these fourth group elements will have 4 electrons in the outermost. 4 electrons in the outermost. That makes this element something special actually. So all these fourth group elements are called as semiconductors. They are called semiconductors except carbon. Except carbon. Silicon, germanium, tin, lead, Fi, this is some other material, I don't know what it is. So these are semiconductors which are in the fourth group of the periodic table. Why they are in fourth group? It's obvious that the valence electrons will be 4 in that. So what is valence electrons, guys? Can anybody comment what is electron? Suppose if I say silicon. So can anybody say what is the atomic number of silicon? Atomic number of silicon? And also germanium. Atomic number of silicon and germanium. Come on guys, tell me. Atomic number of silicon and germanium. Silicon is 14, germanium is 32. This all known to you, right? So 14 means, what is this 14 tells you? Yeah, that's correct. What is this 14 tells you? 14 are the number of electrons in the silicon atom. In one silicon atom, there are 14 electrons. Similarly, this 32 tells you one germanium atom will have 32 electrons. So how they are arranged? This is as 1s2, 2s2, 2p6, 3s2, 3p2. So 10 and 4, 14 electrons. In the first orbit, there are 2 electrons. In the second orbit, there are 8 electrons, but they are split into 2 parts. As in S subshell, there are 2 electrons. In P subshell, there are 6 electrons. In the third orbit, which is very, very important for us, having 4 electrons. In S subshell, there are 2. In P subshell, there are 2. So total 4 electrons in the third orbit. So there are 3 orbitals in the silicon. Similarly, in germanium, if you see 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. You see here, first orbit 2 electrons, second orbit 8 electrons, third orbit 18 electrons, fourth orbit, which is very important, is 4 electrons. So this is very important. So the last orbit, any semiconductor atom is having 4 electrons. That's why it is called fourth group element. It is arranged in the fourth group of periodic table. Okay, this is what called as electronic configuration. So this point is very important here to know that it is having 4 electrons in the outermost. This point is very important for us. Because it is having 4 electrons, it takes covalent bonding with the neighboring atoms and bonds with the other atoms in the semiconductor and forms a crystalline structure. So that structure also I will show you quickly. And it is also important to know other group elements also here, like fifth group and third group, because fourth group is semiconductor. Okay, fifth group and third group, as the name tells you that in this fifth group every atom will have 5 electrons as the last orbit electrons. Valence electrons will be 5. Similarly, in third group valence electrons will be 3. Boron, aluminum, gallium, indium, thallium, nitrogen, phosphorus, arsenic, antimony, bismuth, etc. are the fifth group elements. So it is also important to know why these third and fifth group are to discuss, because they are going to play a very important role when you want to dope the semiconductors. Doping of semiconductors, once again I will talk about this. But my point is, fourth group elements are very important because they are semiconductor atoms. Now, so this is the basic structure of every atom. As I just shown you, there are 14 electrons in silicon and 32 electrons in germanium. You can see here in first orbit 1, 2, in 2 electrons. In the second orbit there are 8, 1, 2, 3, 4, 5, 6, 7, 8 electrons. In the last orbit, this is important for us. This is important, 1, 2, 3, 4 electrons in the last orbit. Similarly, germanium also, if you see, first orbit, this is first orbit, this is second orbit, this is third orbit, and this is fourth orbit. How many electrons? 1, 2, 3 and 4. So 4 electrons in the outer orbit. So both the atoms will be semiconductor atoms because they have 4 electrons. Now the question is this having only 1 electron? Sir, if we add 2 plus 4, 4 plus 6 group elements, what happens? 2 plus 4, 4 plus 6 means, I didn't understand, Kranti. Sir, why we are going only with silicon and germanium, why not with others from group 4? Good question. Kranti, I didn't understand your question. Can you please little elaborate? I will answer. By the time I will answer Chetan question. Chetan, if you see the periodic table, from top to bottom, if you go, top to bottom, carbon atomic number is 6, right? So that means only 6 electrons are there. Silicon is 14. Germanium is 32. Then tin is 50. So as you are moving from top to bottom, the size of atom increases. Similarly, even you see in fifth group also, 7, 15, 33, 51. So size increases. If you go from left to right, the number of electrons increases. Here 5, 6, 7, 8, 9, 10, like that. So 13, 14, 15, 16, 31, 32, 33, 34, like that. So my point is, as you move from top to bottom, the size of the atom increases. Size of silicon atom is smaller than germanium atom. That's what you can even see here. The size of silicon atom is smaller than germanium atom. Germanium is bigger. When atom size is bigger and bigger, the attraction of nucleus for the last orbit electrons will be lesser and lesser. These electrons are lightly attached to the nucleus than these electrons in silicon. So it requires more energy to bring these electrons as free electrons than in germanium. In silicon, it requires more energy. That means these electrons are strongly bound to the nucleus. These electrons are loosely bound to the nucleus because they are far from the nucleus. Because after all, what is this nucleus? It is positively charged. This is negatively charged. So attraction becomes lesser and lesser as you go far and far. Epsilon naught, epsilon r by, so that's what, sorry, what is that? the what we call it as, I forgot. As this distance increases, attraction force between these two, F1 F2 by what we call it as that, I just forgot that. So as this increases, as the distance increases, the attraction force, I mean the force of attraction decreases. So it is easy for these electrons to come out. Similarly, if you go for other atoms other than this germanium, suppose if you go for tin, it is much bigger than germanium. So it will become much easier for that atom to lose the last orbital electrons. Such electrons, the electron, if at all it comes out, this electron comes out, this becomes free electron, and this electron will contribute the current. Such current, because of this external energy, if they are coming and becoming free, because of temperature, if they come out and they become free, they contribute some current. That current we call it as, such current we call it as leakage current, thermally generated charge carrier current. Thermally generated charge carrier current we call it as, and we don't want such current. So it is the reason germanium is having more leakage current than silicon. Germanium will have more leakage current than silicon. That's why silicon is more used. If you go for some other atom, that will have much more leakage current, which leakage current is what? Unwanted. Leakage is always unwanted, right? That's the reason we don't want. Understood? Chetan, did I answer your question? Now, Satyasri, that is also another reason. Silicon is availability is also abundant. So that is also another reason. Hemant, if you take carbon is not a semiconductor at all. Since it is having 4 electrons in the outermost, it is in the 4th group, but it is not a semiconductor. Then why it is in 4th group? Because it is having 4 electrons. Then why it is not semiconductor if it is in 4th group? If it is having 4 electrons? Because the energy gap is much higher than 1 electron volt. The carbon energy gap is not close to 1 electron volt. That's why carbon is not a semiconductor. Then Hemant Krishna, yes, silicon is having more thermal stability. That's what. What is thermal stability means? Because of temperature, leakage current will be less in silicon. That's why it is better. Kranti is asking, sir, for P type we add 4 plus 3 group, okay, element. If we add 2 plus 4, acha. You want to add second group elements instead of 4th group, na? Can you please remind me when we talking about N-type semiconductor and P-type semiconductor, just maybe next half an hour I will be speaking about that, because that is the time you can exactly understand why we use 3rd group and 4th group. This is a good question actually. It's a very nice question, Kranti, that you are asking this question, that why to add 5th group elements only to get N-type semiconductor? Why do you add 3rd group only? If you add 6th group element, you will get more electrons, right? It looks like that. But actually not. I'll tell you the reason why. Okay. So if I forget also, please Kranti remind me. During N-type semiconductor and P-type semiconductor, I'll tell you and I'll justify why it is. Why only 3rd group? Why only 4th group? Why not 5th group? Why not 6th group? Why not 7th group? This 5th group atom will have 5 electrons. That out of 5, 4 will take the covalent bonding. One electron will be donated. So extra electron becomes a free electron and you are getting electron. What if you add 6th group element? You will get 2 more electrons, na? 7th group 3 more. It looks like that, but it's not going to happen. I'll tell you the reason and justification a bit later. Okay. Yeah. So this is the basic structure. But my point here is very important. All of you attention here. That in a semiconductor, not only one atom, na? Suppose if I say it is a semiconductor material, silicon or germanium, it will have plenty of atoms, not only one atom. One atom looks like this maybe, and that also not like this exactly. This is a 2-dimensional representation. Actually, atom is of 3-dimensional. Yeah, if you go for a material, how many atoms will be there? Plenty, right? Per centimeter cube, how many? 5 into 10 power 22 in silicon it is. Those many atoms are there. How all these atoms will be there? They are all in this covalent bondings. Because every atom tries to become stable by having 8 electrons in the outermost. But in silicon or in germanium or in any semiconductor, they are having only 4 electrons in the outermost, and they want another 4 electrons to have stability. That's why any atom cannot lose 4 electrons, any atom cannot accept 4 electrons, because every atom is having 4 electrons only. Suppose if any atom is having 5 electrons, out of 5 maybe 1 electron can be donated, but every atom here is having 4. So no atom is ready to donate, no atom is ready to accept. That's why sharing of electrons happens. Okay, sharing of electrons happens. That sharing of electrons is called as covalent bonds. Okay, this is how it is. So this atom having 1, 2, 3, 4 electrons, and this is another atom 1, 2, 3, 4 electrons. Now there is a bonding between these 2 electrons, sharing these 2 electrons. These 2 electrons are shared. And similarly, there are 4 electrons for this atom as well, 1, 2, 3, 4, and these 2 electrons are shared by these 2 atoms. These 2 atoms are sharing these 2 electrons. Similarly, these 2 electrons. Similarly, these 2 electrons. Now see, for this atom, this central atom, having 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons in the outermost, it is stable. For getting stability, these atoms will try to have 8 electrons in the outermost. Suppose if an atom is having 7 electrons in the outermost, it try to accept an electron so that it becomes stable. Suppose if it is having 1 electron in the outermost, then it always want to lose that electron so that the outermost electrons will become 8. But here in this case, sharing happens and atom becomes stable. What about this atom? This atom also will have covalent bonding with the neighboring. This atom also will have, this electron also will be shared by another atom like this. So this all continuous, because not only 1 atom or 4 atoms or 8 atoms, there are plenty of atoms. So how these atoms you can imagine? Imagine this big room, okay, imagine this big room as a semiconductor block, and imagine if this room is filled with full of oranges. So every orange is like an atom, so it is full of oranges. So similarly, semiconductor material is full of atoms. How all those atoms are there? They are all in the covalent bondings, and that structure looks like this. Now you guys, you can see this is a covalent bonding here. This is a covalent bonding. 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 And this structure we call it a crystalline structure, and it is at 0 Kelvin. It is at 0 Kelvin. At 0 Kelvin, all the atoms are in the crystalline structure having covalent bonds with the neighboring silicon atoms or germanium atoms. All are silicon atoms are all germanium atoms, equally applicable. Okay, because every atom is having outermost 4 electrons. So the point here is all the atoms are sharing the electrons, and all the electrons are bound to nucleus and the covalent bondings. That's why there is no free electron available here. There is no free electron. When there is no free electron, no current is possible if you apply even electric field also. So there is no current possible. That's why at 0 Kelvin, this semiconductor behaves like insulator. Insulator. Semiconductor behaves like insulator at 0 Kelvin because there are no free electrons. If you want to have conductivity, there must be some charge carriers available. Here no charge available, electrons are available. Remember, there is a difference. Electrons are there. It doesn't mean there should be current. Even in this insulator also, this is an insulator. In this insulator also, electrons are there, but there are no free electrons. Similarly, in semiconductor at 0 Kelvin, electrons are there plenty, but they are not free. They are bound to nucleus and covalent bond. That's why they are not free. That's why there is no current. That's why they are called, they behave like insulator. What is that? Semiconductor behaves like insulator. Clear? Now, the same structure, this is in terms of covalent bonds and atoms, right? So this is what we call it as bond model. Bond model. Covalent bond. This is what called as band model. Energy band model or simply band model. Because now we are expressing the same semiconductor in terms of energy bands. Yes, Hemant Krishna, exactly. Valence electrons are there, but they are not free. They are in the covalent bond. That's why they are not free. Okay. This is what energy band diagram, just already you have seen. This is EV and this is EC. See, these are all the electrons what I have shown here, right? These are all the electrons dotted. are nothing but these electrons, whatever here. Every electron is having different energy. The range of different energies of these electrons is represented here in the covalent bonds, sorry, in the valence band. So these are all different energy levels. In fact, these are all different energy levels. At different energy levels, different electrons energy is represented with dots. So these dots here in the energy band diagram are not electrons, remember. These dots corresponds to the energy of the electrons, because this is the energy axis. Remember, this is the energy axis. So we are talking in the energy band diagram, energy of an electron. Suppose, for example, this is the clarity you have to get, guys. Later, otherwise you will get confusion. All of you remember, this is the clarity you have to get at this stage only. That's why I am emphasizing here, because as we go forward, you have to have that clarity. Here we are showing lot many electrons, right? But every electron is having different energy. No two electrons in the semiconductor will have same energy. As per Pauli's exclusive principle, when electrons are in the system in a material, no two electrons can have the same energy. Every electron have different energies. If I arrange all these energies of these electrons in a graphical form, that looks like this. So these are all different energy levels available. So different electrons at different energy levels. The range of these energy levels from here to here, the range of energy levels of these electrons in the covalent bond, understood? The range of energies of the electrons in the covalent bond in the semiconductor is nothing but valence band. Apart from this, there are some range of energies available empty. These are all the, again, range of energies, different energy levels available but not filled. These are different energy levels available but filled by the electrons. That's why it's shown with dots. These are energy levels available but not filled by the electrons. Such energy levels are empty energy levels are called conduction band. This is empty energy level, empty. If you have electrons, if you have some additional electrons or extra electrons, there is a space, there is a availability. There is an energy level available for the electron to fill. Such energy levels are called as conduction band. So conduction band is nothing but available energy levels, allowed energy levels. Valence band is nothing but filled energy levels. Filled by what? Electrons. What electrons? The semiconductor electrons, valence band electrons. Got it? So that clarity you have to have. And the gap between these two, filled energies and empty energies, the gap between filled energies and empty energies is Eg. It is close to 1 electron volt. It is close to 1 electron. That is the clarity you have to have. Okay. Now carrier generation. Let's talk about carrier generation. What is carrier generation? Suppose this is the energy band diagram of a semiconductor at 0 Kelvin. If some external energy is applied, for example, if external energy is applied, for example, if I go back to this diagram, if some external energy is applied in the form of temperature, then maybe one of the covalent bond is broken and this electron comes out. So that electron will become free electron. This electron is now called as free electron because it has come out of the covalent bond. It doesn't mean that it is coming out of the material, right? It is still in the material only, but it just has come out of this covalent bond. Covalent bond is broken. Why? Because external energy is supplied. How much? Equal, sufficient enough to break the covalent bond. If this energy is not sufficient enough to break the covalent bond, this electron will not come out. If the energy is sufficient enough to break this covalent bond, then covalent bond is broken and electron will come out of the covalent bond. Okay? Come out of this covalent bond. Such electron is called as free electron. Once this electron comes out, the vacancy created here is called as a hole. So the vacancy created is called as hole. Remember, all vacancies cannot be called as holes. The vacancy created by breaking the covalent bond when an electron comes out is called a hole. This is called as a hole. Hole plays very important role here. This is called as generation of charge carriers, electron and hole. as a pair is generated. That's why it is called electron hole pair is called. It's called EHP. Now the question is, once this electron comes out, where this electron goes? Why this electron is coming out? Because it is gaining some energy. Because we supplied some extra energy, this electron must have got that energy gained. That's why it has to move upper to the another energy level. For example, this electron what I am showing here is this electron in the energy band. Let us say this electron. Let us say this electron. Now because I applied external energy, this electron has to come out. Where? Because it gained energy, it has to be some higher energy level, right? Cannot be here. This electron cannot come here because this is forbidden. So this electron has to come here because these energy levels are allowed energy levels. The electron even can come to this level, even can come to this level because these are all allowed energy levels. But first always lower energy levels will be filled and then higher and higher energy levels will be filled. So always remember, electron gains energy, so it cannot be at the same energy level. It will be at different energy level. It will be at different energy level. Where is that energy level? Conduction band. So electron comes here. So the vacancy created here is called as hole. So that's what we call it as electron hole pair. Electron hole pair, EHP we call it as. So the free electron created because of this external energy is available now in the conduction band, and the hole created is available in the valence band. Suppose if this external energy sufficient enough to break another covalent bond, so another electron will come here, another electron will occupy here, another hole will be generated here. So the number of electrons created are equal to number of holes. That's why they are called electron hole pairs. They are created as pairs, not single electron or hole. Got it? Is there energy levels are available in energy gap? No. No. Allowed energy levels are not there. Allowed energy levels are conduction band and valence band. Valence band is filled already, conduction band is empty available. No allowed energy levels in the forbidden gap. That's why it is called forbidden energy gap or simply energy gap. Why there is no energy level in the band gap? You know, when atoms are coming closer to form this covalent bonding, the energies of these electrons are split into two parts. All allowed energy levels and empty energy levels, filled energy levels and empty energy levels. That formation I am not explaining here. It takes another half an hour, 45 minutes. Okay. So this is very important. So conduction, this is what generation is. Generation means carrier generation is a process where electron hole pairs, EHPs, is simply called as EHPs, are created by exciting an electron. Exciting by electron is nothing but supplying some external energy to it. From valence band of the semiconductor to the conduction band, thereby creating a hole in the valence band. So by creating electron hole pair, a free electron is available in the conduction band, a free hole is available in the valence band. Got it? That's what electron hole pair we call it as. Then carrier recombination. Yes, once generation is there, recombination is reciprocal to generation. So generation is denoted with Z. This generation is denoted with Z. Recombination is nothing but, you know, suppose if external energy is applied like this, electron is available here and a hole is available here. Now if energy is removed, the electron will come back and occupy this hole. So here there is no electron and here there is no hole. This process of merging this electron with the hole, process of merging electron with the hole, process of occupying the hole by an electron is called as recombination. That's what here it is said. No, recombination is the process of merging of an electron from the conduction band with a hole in the valence band. Okay, and remember, very important point here, when electron gains energy, generation happens. Generation results electron hole pairs creation. Recombination results electron hole pair disappearance. There is no electron hole pair available after recombination because electron recombined with the hole. There is no free electron, there is no hole available. So that's what here must be. When electron falls from the conduction band into the valence band into a hole, a recombination process occurs and the electron hole pair disappears. Once recombination happens, electron hole pair will not be available. These all concepts, remember guys, These all concepts are very useful understanding, even PN junction also, BJT also, MOSFET also, capacitor also. Formation of PN junction depends on this recombination process as well. Diffusion, drift, all these things will come there also. Okay. So these are all building blocks to understand the devices, in fact. That's why it is called semiconductor basics or semiconductor physics. So we understood generation, we understood recombination. So I just already told you what is hole. Hole is nothing but the vacancy created. Guys, remember in the valence band, sorry, in the conduction band, already plenty of vacancies available, right? These are all vacancies only. They are not called as holes. The vacancy created in the semiconductor by breaking the covalent bond is only called as a hole. Vacancy created is called as a hole. Okay. So suppose if this electron comes out, so here is a vacancy created. This is called as a hole. Suppose if this electron comes and occupies this process is called as recombination. And since this electron coming and occupying this, here is a hole available, here is no more a hole available now. And this is again called as hole because it is created because covalent bond is broken. It has been created. Okay, similarly, suppose if this electron comes and occupies this, here there is no hole and no free electron. So hole is now created here. Okay. So hole is created, not available always, by breaking the covalent bond and because of electron only obvious, right? So this is what called as hole. And see, very important point, initially if electron moves here and one electron is moving here, for example, if at all, and there is a hole created, right? Now again electron is occupying here, so hole is here. Another electron is occupying here, hole is here. So if you see another way, hole was here and it is moving here. Now from here to here it is moving. So actually electron is moving here like this, but opposite to that hole is moving. This is what the movement of hole is, or current due to hole is. So in fact current due to hole is nothing but current due to the bound electrons or covalent bond electrons. Because this electron is moving from here to here, there is a hole. Because this electron is moving from here to here, here is a hole. So this hole is moving from here to here because electron is actually moving from here to here. But this electrons, then the question may come to you that, sir, it is actually because of electron, then why we talk about holes only? Why can't we talk about electrons? Because when we see the p-type semiconductor, these type of vacancies are plenty available than the bound electrons. So then it is easy for us to speak in terms of holes than in terms of bound electrons. Like in n-type semiconductor, there are plenty of electrons in the conduction band. So it is easy for us to speak in terms of electrons, free electrons than the bound electrons. So it is all the convenience. That's why hole is the vacancy created by an electron and it moves opposite to the electron always. It moves opposite to the electron always. In fact, hole movement is nothing but the current due to it is nothing but, hole movement is nothing but the electron, bound electron, covalent bond electron movement it is. Hole movement happens because a bound electron is moving, covalent bond electron is moving. Okay, remember that. So this is what the whole current is, I just told you. Now current as you all know, current is the charge carriers. Can you guys define current? You must be knowing, right? What is current? Current happens when there are three conditions satisfied in any material. One is there must be some electric field applied or potential difference. Potential difference will have an electric field across it, and there must be a closed loop, and there must be charge carriers. If these three are there, there is a current. But in solid state material, generally we prefer to speak in terms of current density. So what is current density? Current density is J. J is current per unit area. Per unit area, how much is the current? Because how much is the current also depends on the size of the device, size of the material. So it is appropriate to speak in terms of current density than in terms of just current. So current per unit area is current density. So that is for any material, J is equal to Q into N into mu into E it is. That's what I said. To have the current, we have to have three things must be satisfied. One is potential difference must be satisfied. So this is what potential difference, okay. If you have potential difference, then there will be electric field. And the second thing is there must be a closed loop. So if you want to have the charge carriers to flow, there must be a closed loop. Assume there is a closed loop. And the third thing is charge carriers. Here in this case, electrons. So these electrons having a charge q, these n tells you the number of electrons in fact. So these many number of electrons having a charge q moving with a mobility mu, when there is an electric field present, results a current per unit area, and that is called as J, right. But this is for any material we can apply, but of course insulator doesn't have any current, that's why it is for conductors we can say. But in semiconductors, this equation is slightly modified. Just now we spoke about free electrons which contributes the current. So current due to electrons is like this, sorry, this is current due to holes. So current due to electrons is like this, or current density due to electrons is like this, as like conductors, same like conductors. But there are other currents are also possible in semiconductor, which is due to the holes. This is due to free electrons in the conduction band, this is due to free electrons. But there are other currents also possible in the semiconductor, which is called as hole current. In fact, it is covalent bond current, covalent bond electron current. But it is convenient to speak in terms of holes, that's why this is called hole current. So that's why the current due to holes is Q P mu P into E, where P is number of holes and Q N mu N into E is N is number of electrons. So the total current in a semiconductor, total current density in a semiconductor is Q N mu N into E plus Q P mu P into E. Sum of these two currents is the total current happening, isn't it? So that can be written as Q into N mu N plus P mu P into E is the current density in a semiconductor. So that makes the difference between conductors and semiconductors, because in conductors you don't have this current. That is the difference between other materials and this. Hope you understand, guys. Let's move quickly. Done, guys? Any questions? If you have any questions, keep asking me. So intrinsic semiconductor, so far we are talking about semiconductor. Then what is intrinsic semiconductor? The semiconductor having number of electrons exactly equal to number of holes is called as intrinsic semiconductor. That number we generally call it as Ni, which we call it as intrinsic carrier concentration. Ni is called as intrinsic carrier concentration, where N is number of electrons and P is number of holes per centimeter cube or per meter cube, whatever. Why number of electrons and holes are equal in intrinsic semiconductor? Intrinsic means pure semiconductor. Why they are same? Can anybody say, guys, why? Why electrons and holes are same in number? Can anybody say, guys, why they are same in number? Come on. Because electron holes are generated as pairs. Electron hole pairs are generated always, isn't it? Not Coulomb's law. Electron hole pairs are generated. Intrinsic semiconductor, what the semiconductor so far I have shown is intrinsic semiconductor only, having all covalent bonds, and at 0 Kelvin no free electrons, so it behaves like insulator. But at higher temperature some free electrons may be available and holes are also available, so it behaves like conductor and whose conductivity can be defined. Now we want to go for some doping. Why doping is required? So this doping is nothing but what and why doping is required. What is doping? First of all, doping is nothing but adding impurity to the semiconductor. So for example, this is the bottle, okay, it is pure water. If I add a glass of orange juice to this water becomes impure, extrinsic. Similarly, adding impurity to the intrinsic semiconductor makes the semiconductor extrinsic, impure. And that process of adding impurity is called as doping. Doping means adding impurity, the process of adding impurity. Now the question is why? Why to add the impurity? Already pure semiconductor is there, why you are spoiling that? The point is to have some parameters in our control. In intrinsic semiconductor, if you see, J is equal to, just now we have seen, in intrinsic semiconductor, J is equal to Q into N mu N plus P mu P into E is the expression we have seen. This is the current due to electrons and this is the current due to holes. Now, since it is intrinsic, the number of electrons exactly equal to number of holes, which is equal to number of intrinsic carrier concentration, we call it as Ni. So, I can write this as Ji. Intrinsic semiconductor current density is equal to, N is equal to P, if I substitute Ni here and here, so it is Q into Ni into mu N plus mu P into E. This is the current density. Now I can write from this what is conductivity, which is Q into Ni into mu N plus mu P. Conductivity into electric field is current density. Okay. So this is the conductivity. Just a second. This is the conductivity. Okay. This is the conductivity. But now see, this Ni value generally in the order of 10 power, for silicon if I say it is 10 power 10 it is. Charge of an electron is known. If anyone is having calculator with you, please type this. Charge of an electron is 1.6 into 10 power minus 19. Ni is 1.5 into 10 power 10. Mu N is 1350 for silicon. Mu P is 480 for silicon. If you substitute and check this value, this is conductivity of intrinsic silicon. Come on guys, can anybody check this? It's going to be very close to 0 guys. Check it otherwise. 1.6 into 10 power minus 19 into 1.5 into 10 power 10 into 1350 plus 480. You check this, you will get this value close to 0, 0.0000 something. That means the conductivity of intrinsic semiconductor is very, very low. That means it is behaving like an insulator even at room temperature. At 0 Kelvin, of course it is insulator. But even at room temperature, it is behaving like an insulator. Come on guys, someone please do this calculation and tell me. Conductivity of intrinsic semiconductor for a silicon at room temperature is close to 0. That means it is like an insulator. But if I want some conductivity, if I want this semiconductor to behave like a conductor or the conductivity as I wanted, very important is conductivity as I wanted if I want, that is the reason I go for doping. The possibility of increasing the conductivity here is, see what is Ni? Ni is nothing but N or P. So either you go for N increase or P increase, then only you can increase the conductivity. Act as insulator exactly, right? So to increase the number of electrons or to increase the number of holes, we go for doping. Why to increase this number? Because that conductivity depends on that number only. So we want more conductivity or less conductivity depends on that number. That number should be in our control. That is why we go for doping. Okay. Now see how this doping is. Yeah, this doping is of two types as you know. Extrinsic semiconductors are of two types, N type and P type. We'll get these extrinsic semiconductors based on what type of impurity you are adding. This is the fourth group elements except carbon, don't consider carbon. Silicon, germanium, tin, lead are the semiconductors, but out of them silicon and germanium are used for the reasons already I told you. Now for this fourth group element, these are intrinsic semiconductors, right? For these fourth group elements, I want to add either fifth group or third group. Now I am going to add fifth group element. Maybe nitrogen is added to semiconductor. maybe nitrogen is added to silicon, or nitrogen added to germanium, or phosphorus is added to germanium, whatever. So this is having 5 electrons in the outermost, this is having 4 electrons in the outermost. Then what happens? You see, in the same way, if you do like this results n-type semiconductor. Suppose if you add third group elements into fourth group elements, that gives you, this is also called doping, that gives you p-type semiconductor. So why it is called n-type, why it is called p-type, I will explain. Okay. So let's see now how this with covalent bond diagram, let's understand how this doping happens and what the difference makes this, how it happens. Let's see that. Before that, one information that guys, 15 marks in just 15 hours. Complete general aptitude session going to come by Rakesh Talreja sir, your favorite Rakesh Talreja, to gain 15 marks within 15 hours of teaching, of revising these topics. Please share this information to rest of the students. Okay. And another session is Maths Marathon, exclusively on mathematics only, by Ankit sir and Rakesh sir together. They will be together, like me and Sanjay sir are taking this EDC. Rakesh sir and Ankit sir are going to take this Maths Marathon session. Is also going to come after this marathon sessions are over. Yeah, now n-type semiconductor. As I just told you, imagine these are all semiconductor atoms. Okay. Out of these semiconductor atoms, now see, one phosphorus is added, only one phosphorus. Assume one phosphorus is only added. What we discussed just now, phosphorus will have 5 valence electrons, right? See here, this is the phosphorus. It is now added among the so many silicon atoms. How many silicon atoms? Let's say per centimeter cube, 5 into 10 power 22 are there. One phosphorus I have added. Just like an example I gave you, this room of oranges, full of oranges it is. But now I am just adding one apple into this room. So that apple is now surrounded by so many oranges. So phosphorus situation is also like that. Phosphorus is an atom now surrounded by so many silicon atoms, or so many germanium atoms, whatever. Where phosphorus is having 5 valence electrons, right? Let's see what are they. This is 1, 2, 3, 4 and 5. 5 valence electrons it is having. Now even phosphorus also wants to become stable, so it also have to have 8 electrons in the outermost. So what phosphorus will do? Will try to bond with the covalent, bond with the neighboring atoms. How many? It need only 4 silicon atoms to bond with, right? So it will take a covalent bonding with this silicon atom and this silicon atom, this silicon atom and this silicon atom. So 4 covalent bonds are taken with 4 neighboring silicon atoms by phosphorus, leaving this electron. Guys, remember, this electron is not a free electron, it is extra electron. There is a difference, guys. The electron, the 5th electron of the phosphorus is extra for it. It doesn't need it because it's already become stable. So this electron can be easily donated by the phosphorus. Even if you apply small external energy, the electron can come out easily. Why? Because that electron doesn't need. That electron is not needed by the phosphorus. It is an extra for it. So it can easily lose it. One phosphorus, if I add one extra electron, if I add 10 phosphorus, 10 extra electrons. If I add 10 power 10, 10 power 10 extra electrons are available. These are called extra electrons, not free electrons, guys, remember. Is it clear? Now another very important part. See, this is how it happens. Once you add the phosphorus, to the phosphorus is pentavalent atom. Pentavalent, why 5 electrons it is there. Pentavalent atom to the semiconductor. It looks like this. Now what happens is, let's see this same situation in the energy band diagram. Same situation in energy band diagram. See, same situation. This is a phosphorus. Let me use the same colors. This is a phosphorus. 1, 2, 3, 4, 5. 5 electrons. Out of that, this is bond, this is bond, this is bond, and this is bond. And this is what the extra electron we are talking about, right? This is extra electron. Now that electron also will have some energy corresponding to. The energy corresponding to the extra electron of the phosphorus is somewhere here, guys. This is somewhere here. And that energy corresponding to the fifth electron of the phosphorus is called as ED. Is called as ED, donor energy level. That means the energy of the phosphorus electrons will have this much energy, and that energy is close to conduction band energy of the semiconductor. Conduction band energy of the semiconductor, remember, the energy of the electrons which are the fifth electrons or which are the extra electrons of phosphorus will have energy close to conduction band energy of the semiconductor. And that energy level which is close to conduction band of the phosphorus atom is called as donor energy level, because it is ready to donate. Understood? Now guys, as someone is asked, I think Kranti or someone asked me, why fifth group element, sir? This is one of the reasons, guys. This is one of the reasons that the energy of the extra electron should be close to conduction band. There is no guarantee that seventh group elements or sixth group atoms will have the energy of that extra electrons close to conduction band. Somewhere else it is. And another point is, suppose if you are going to add seventh group element, for example, you may be thinking that 4 electrons will be taking covalent bond and 3 electrons are extra, they can donate 3 electrons. Here after all only 1 electron is donated. If you add 7th group element, it can donate 3 electrons, now it is better. You will get more electrons. But it is not going to happen. Why? If an atom is having 7 electrons in the outermost, it will not lose 3 electrons, rather it will gain 1 electron and become stable. It is easy for that atom to gain 1 electron and become stable. Not easy to lose 3 electrons and become stable. That's why 7th group element will not donate electrons. So these are the two reasons why we go for only 5th group. 5th group is only because the extra electrons energy is very close to conduction band energy. So what, sir? So what? This electron is now loosely attached by the phosphorus. So what? If you apply small energy also, small external energy, if you apply very small external energy, not even room temperature, if you apply even small energy, not even room temperature, suppose if there is an electron here, let's say this electron, covalent bond electron, let's take covalent bond electron, let's say this electron. If you want to bring this electron out, that covalent bond has to be broken. That means this electron to come from here to here in the conduction band, it has to gain this much energy. How much? Close to 1 electron volt is the energy must be required. So if you want to make this electron free, you have to apply minimum 1 electron volt. What if this electron to come to here? How much is the energy required? Fraction of this 1 electron volt. That means even small external energy is sufficient for this electron to become free. So even at room temperature, this electron can easily come out and becomes free. So this is called free electron now. This is free electron. Understood? So pentavalent atom, once you add at 0 Kelvin, it will not have any free electrons. So n-type semiconductor is also at 0 Kelvin 0. It is as insulator. But even at higher than 0 Kelvin, not even at room temperature, it can have this electron as free. Whereas in intrinsic semiconductor, the energy, minimum energy required is 1 electron volt. Yes, Hemant, exactly. Now one phosphorus atom, if I add, 1 free electron is possible with very small energy. Suppose if I add 2 phosphorus atoms, 3 phosphorus atoms, 4 phosphorus, like this. So all these electrons can easily come to conduction band and become free with very, very small energy. With this free electrons are available with even that small external energy. But second point to note is, with this free electrons, are there any holes created? Are there any holes created? No holes created, guys. Because covalent bond is not broken. This electron is coming out, becoming free. Covalent bond is not broken. Hole is not created. So there is no hole created. Hole is always created in the valence band only. Valence band electrons are not coming to the conduction band. Extra electrons are coming to the conduction band. These extra electrons are becoming free electrons. That's why number of electrons, how many are coming? How many are coming? How many are the free electrons in the conduction band now? Equal to the number of atoms you are adding. Each atom donates 1 electron. If I add 1 atom, 1 electron is possible. If I add 10 atoms, 10 electrons. If I add 10 power 10 atoms, 10 power 10 electrons. So that number of atoms what we added is denoted with Nd. Nd is called donor concentration. Donor concentration. So now I can define how many are the number of electrons, isn't it? How many are the number of electrons I can define, right? How many are the number of electrons I can define? Isn't it? Because how many are the phosphorus atoms to add I can define. If I add 20 free electrons, no holes. But if you come to room temperature, this type of electrons also will come into picture, na? That type of electrons also come into picture. Of course, that will come. That number is called as Ni. So the total number of electrons at room temperature, we can call it as Nd plus Ni. But this Nd will be very, very large compared to this number, because this number will be generally in the order of 10 power 16, 10 power 15, 10 power 17, whereas this number is in the order of 10 power 10. So you can neglect this number compared to that Nd. So number of electrons is almost equal to Nd only. Okay. So at room temperature, I can say the conductivity is equal to, or current density is equal to Q into N mu N plus P mu P into E I can write, but I can change this as Q into N mu N into E, assuming there are no holes. But holes also will be there, but it is approximately I can say, because I am neglecting the holes. Holes are very small in number. The holes in n-type semiconductor are due to only temperature, due to only at room temperature or higher temperature. But the number of electrons are primarily because of the doping you have done. Understood? So number of electrons will decide how much is the current density or how much is the conductivity. Similarly for p-type semiconductor. So electrons are called as majority carriers and holes are called as minority carriers because they are very small in number. This is known. Same is the case for p-type. P-type is we are adding boron as an impurity. Boron will have 3 electrons only, 1, 2, 3 only, and here is a vacancy. Here is a vacancy, it is not a hole. It is a vacancy added, it is not a hole. Like extra electron, this is a vacancy, it is not a hole. And the energy corresponding to that vacancy will be close to valence band. Close to valence band, that energy is called as acceptor energy, because this atom accepts an electron. Now see, for this electron, it is easy to occupy this energy level because it is also vacancy. Now maybe this electron will come and occupy this. Instead of going to all the way from here to here, it needs lot of energy, 1 electron volt. Whereas for this electron, it is easy to occupy this level. The moment this valence electron goes and occupies this level, here is a hole created, here is a hole created, here is a hole created, here is a hole created. Such holes are available in the valence band. How many? Equal to the number of acceptor atoms you added. So number of holes available here is equal to the number of acceptor atoms. So the current density can be read is Q into P into mu P into E approximately, because N is almost 0. But number of electrons are also will be there because of temperature. Some electrons may be available in the conduction band also. So that number is Ni. Understood? Yeah, Na it is. So majority carriers are holes here. Holes are the majority carriers, electrons are the minority carriers. You know the meaning of minority and majority. right? Then compensated semiconductor. Suppose if I have an intrinsic semiconductor, if I add with donor concentration, then it becomes N-type semiconductor. No, if I add with acceptor concentration, then it becomes P-type semiconductor. If I add both, pentavalent, trivalent, both if I add it to the intrinsic semiconductor, that is called compensated semiconductor. Then what type of semiconductor it becomes? Whichever is higher. If ND is higher than NA, then it becomes N-type semiconductor. If NA is higher than ND, it becomes P-type semiconductor. If ND is equal to NA, it remains as intrinsic semiconductor only. So such semiconductors are called as compensated semiconductors. Remember, compensated semiconductors. Compensated semiconductor, just I have told you, N-type it is if ND is NA greater than NA, it is P-type if NA is greater than ND. If this is equal, then it remains as intrinsic semiconductor only. Yeah, current density I just told you already. This is the equation, current density J. Yeah, I can write the conductivity equation from this. Sigma is equal to Q into Ni into mu n plus mu p is the conductivity equation. So, or this we can write it as sigma into E, where sigma is this. Okay, this is for intrinsic semiconductor. Ni stands for intrinsic. So, if the same thing, conductivity, I just wrote this as Q into Ni into mu n plus mu p is the conductivity, intrinsic semiconductor. Current density of N-type semiconductor is this. This Nn suffix it is, please make a note of this, this is also suffix. This Nn indicates number of electrons in N-type, Pn indicates number of holes in N-type. So, these are very, very small. So, I can write this Jn as Q into Nn into mu n approximately, assuming this number is small, since Nn is far, far greater than Pn. Okay, we can write like this. Similarly, conductivity equation is this. This also please write it as P for N-type, na Pn it is. Please forgive. So, we can write this sigma n is almost equal to Q into, for P-type or N-type it is, N-type, na, it is Nn. For N-type semiconductor, na, it is Q into Nn into mu n. This is the conductivity equation approximately, because Nn is far, far greater than Pn. Is it clear, guys? Are these equations? So, these equations are very important, pretty important for you. Then current density of P-type semiconductor, similar equations. So, this is general equation where Np is far, far smaller than Pp here, or Pp is very, very high. So, here also this Pp it is Pp, okay. Yeah, next another important rule or the law is mass action law. It is very simple, Np is equal to Ni square. Product of N and P is equal to Ni square is a constant, and it is independent of temperature. At a fixed temperature, it is independent of donor impurity or acceptor impurity. That means it is valid for intrinsic semiconductor, N-type semiconductor and P-type semiconductor as well. So, it is going to be very, very useful in further discussions. You must be aware, all of you. Are you guys? Mass action law, you are aware? Yes. Charge neutrality. So, this is the charge neutrality condition expressed by equating the density of positive charges and negative charges. The total positive charges in the semiconductor must be equal to the total negative charges. So, this is the total negative charge and this is the total negative charge. Na is total number of acceptor atoms, right? Since acceptor atoms are accepting the electrons, it becomes negatively charged ions, and N is number of electrons. So, the total negative charge is sum of these two. Similarly, total positive charge is this. So, from mass action law, Np equal to Ni square. So, I can write what is P here. Okay, P is equal to Ni square by N. So if I substitute that, N plus Na is equal to P is Ni square by N plus Nd. So now if I can arrange everything in terms of N, because equation is now in terms of N, and if I simplify for N, I am going to get the electron concentration equation from this. So actually this equation is derived from this only. This becomes a quadratic equation, and simplify that, you will get the solution as like this. So the number of electrons, how many in an n-type semiconductor, can be found from this, because we know in n-type semiconductor, electrons are the majority carriers. Okay, electrons are the majority carriers. So how many are they? These many. You can find from this. Similarly, the whole concentration can be found from this equation. So if you express this equation from N into P is equal to Ni square. So if you write what is N is equal to Ni square by P, right? If I substitute N there, the entire equation becomes in terms of P, and solve for P, you will get this equation. I am telling you the method. If you have time, you can do, but at this point of time, don't do all these derivations. It is important to know this equation, very important. So you can find how many are the electrons or how many are the holes from these two equations. Very important, guys. Next very important topic is Fermi-Dirac function or Fermi energy level. So this starts with the Fermi-Dirac function. Fermi-Dirac distribution function tells you the probability that available energy state E will be occupied by an electron at absolute temperature T under conditions thermal equilibrium is given by Fermi-Dirac function. Anything understood? It is a book statement. Okay, in a book the statement will be written like this about Fermi-Dirac distribution function. In simple, I will tell you what is this Fermi-Dirac distribution function tells you. It is a function which tells you the probability f of E. It is denoted with f of E. It is a function, tells you function of some energy, right? F of E. It tells you the probability. What probability? Probability of an energy level, an allowed energy level otherwise, occupied by a particular electron. So if there is an electron, what is the probability for that electron to occupy a particular energy level is given by the Fermi-Dirac distribution function f of E. It tells you the probability. Okay. Fermi-Dirac distribution only gives the probability of occupancy of the state at a given energy, but doesn't provide any information about the number of states available at there. How many are is not provided, but tells you the probability of occupying that particular energy level. That's what Fermi energy level. Yes, Hemant. How this Fermi-Dirac distribution function is given? This one. F of E equal to 1 by 1 plus e power E minus EF by KT, where EF is the Fermi energy level, E is a particular energy level at any energy level with reference to EF. That's what EF can be taken as a reference energy level. Above EF and below EF, what is happening we can find. And K is a Boltzmann constant and T is temperature in Kelvin. So if you plot the graph, between f of E and E for different temperatures, okay, at different energies. Suppose if E is greater than EF, let's say at T is equal to 0, at T equal to 0, if E is greater than EF, what is this f of E becomes? F of E is equal to 1 by 1 plus e power E is greater than EF, that means positive value. Okay, positive infinite it is, isn't it? Because T is 0, so positive value divided by 0 is positive infinite. In that case, so what it is? E power infinite is 0 it is, right? E power infinite is infinite, 1 by infinite is 0. Similarly, if E is less than EF, f of E will be 1 by 1 plus e power minus infinite it is. So that gives it is 1 it is. So at E is equal to EF, f of E is 0.5, isn't it? That's what actually plotted. So if you are talking about the probability of energies above EF, it's 100%. The probability of occupying the energies below EF is 0. Yet energy E equal to EF, it is 0.5%, 50% it is. That's what here shown. This is EF, energy is above EF, energy is above EF, the probability is 0. You see, f of E is 0 here, this is 0. And below EF, it is 1. So this yellow color curve, this curve you can see, this is 1 and here it is 0. And here it is 0.5 at E is equal to EF. And this is at higher temperatures T1 and this is at T2 where T2 is higher than T1. And this is at T equal to 0 Kelvin. So this tells you the probability. Of course, from this we'll estimate why this Fermi level is required. Is a lot of discussion can be done here, but due to time constraint I am not able to do that, but I will give you the equations. It tells you, so this is of course the summary of what the points I discussed, but using these Fermi energy levels we can find how many are the number of electrons, we can find how many are the number of electrons or whether it is n-type semiconductor or p-type semiconductor. If it is n-type, how many are electrons? If it is p-type, how many are electrons? All this we can find. So that is the reason why we study about this Fermi energy level. Electron concentration, that's what I just told you. I am not giving you this derivation, can be done from those equations we did, but I will give you electron concentration in conduction band. Electrons obviously available in conduction band. How many are there? N is equal to Nc e power minus of Ec minus Ef by Kt are the number of electrons, where Nc is 2 into 2 pi mn Kt by h square power 3 by 2. This is Nc. Nc is density of states and it is a constant. Similarly, hole concentration, that is number of holes, P is equal to Nv e power minus of Ev minus Ef, Ef minus Ev, Ef minus Ev by Kt, where Nv is density of states in the valence band, which is 2 into 2 pi mp Kt by h square power 3 by 2, where Mn and Mp are effective mass of electron and effective mass of hole. Rest of the constants are known, right? K is Boltzmann constant, T is temperature, H is Planck's constant. Rest of the things are known. So if you know where is the Fermi energy level with respect to EC, we can find how many are the electrons. If you know where is the Fermi energy level EF with respect to EV, we can find how many are the holes, because Nv is known, Nc is known, they are constants. We can find this, isn't it? That's what about Fermi energy levels and the application of Fermi energy level or the requirement of Fermi energy level. Of course, these equations are written, guys, here. So anyhow, so I have also written. This I have already told you. So one more thing, Fermi level in intrinsic semiconductor, just to summarize and give you in brief. For intrinsic semiconductor, it can be proved actually. Fermi level is at the center. Fermi level is at the center for intrinsic semiconductor, or we can say EF, Fermi level is equal to EC plus EV by 2 minus KT minus KT natural logarithm NC by NV. This is the equation. Since NC and NV are almost equal, if effective mass of electron and hole is equal, this becomes 0, then EF equal to, so EF I can say is almost equal to EC plus EV by 2. That is why we will say Fermi energy level is close to center, close to the center we say, KT by 2, sorry, yeah, KT by 2. KT by 2 it is. But anyhow, that term will become 0 approximately when we take NC equal to NV. So EF is at the center, that's what here shown. So this is conduction band and this is valence band. and center is this one. Now similarly, the Fermi energy level for n-type semiconductor would be, Fermi energy level for n-type semiconductor is close to conduction band. You see, Fermi energy level is close to conduction band. So this is somewhere center. This center we can call it as EI or EFI, whatever. So Fermi energy level is close to center, close to conduction band here. So how can I say that? Actually, we can derive an expression here also from the electron, from this equation only we can derive, in fact. From this equation, we can derive this, in fact. EF is equal to EC minus KT natural logarithm NC by ND. This is the expression for EF in n-type semiconductor. So we can say that it is close to conduction band. How close it is depends on doping. More and more the doping, more and more the Fermi level close to conduction band. One more equation I want to give you here, very important equation. One more I will give you. Here, all of you please note. Number of electrons can also be expressed. Let me write little below here. Number of electrons is equal to Ni e power EF minus EI by KT is also the another equation for finding the number of electrons. So we already wrote another equation, N is equal to NC e power minus of EC minus EF by KT. This is also another equation for finding the number of electrons. Then what is the difference? EF is equal to EC minus KT ln NC by ND. That's correct only, na? Yes, Hemant, correct. Chinmay, that's what I wrote, no? Is there any issue in that equation? Natural logarithm I have not written? I have written, yeah. Then what is the difference between this equation and this equation? This equation is depending on EC and EF. This equation is with respect to EF and EI. So using this equation, even you don't know the value of NC and EC, you can still find if you know where is EF. Because EI is always known, it is at center, it is EG by 2, EI is equal to EG by 2 always, isn't it? So this equation is better, easily we can find number of electrons even though you don't know what is NC and what is EC also, yeah. Similarly for p-type semiconductor, so these are n-type semiconductor some characteristics as I just told you. Fermi level for p-type semiconductor is close to valence band, it is close to valence band. How can we say? EF is equal to EV plus KT natural logarithm NV by NA. This is the expression for Fermi energy level. Similarly, we can find how many are the holes using this here as P is equal to NV e power minus of EF minus EV by KT. This is one expression. Another expression I told you is Ni in terms of e power EI minus EF by KT. So where is EI? EI is at center always. This is EI. So using this also you can find how many are the holes, or using this also. The only difference is it is with respect to NV and EV. This is with respect to EI and NI. Okay. So this helps you a lot in finding the equations or current or number of electrons in a semiconductor. So these are some of the characteristics of the semiconductor, n-type and p-type. So how the semiconductor, how in different semiconductor, how the Fermi level depends on temperature. This is also another important thing. You can see here, as temperature increases in intrinsic semiconductor, if temperature increases more and more. So these are the points I think here. In intrinsic semiconductor, as temperature increases more and more, the Fermi level remains at center only. Because as temperature increases, number of electrons as well as holes also increases as electron hole pairs generates in the intrinsic semiconductor. Whereas in n-type semiconductor, as temperature increases, Fermi level moves towards the center, moves away from the conduction band. In p-type semiconductor, as temperature increases, Fermi level moves away from the valence band and moves near to the center. So those are the points here highlighted. Make a note of that. Okay. Other parameters, other semiconductor parameters depending on temperature. Because semiconductor is very sensitive to the temperatures, we need to talk about these parameters. Very, very important parameters. One of them is Ni. How Ni is depending on temperatures? It is Ni square equal to A naught T power 3 e power minus Eg by kT, where A naught is a constant whose value is 2.33 into 10 power 43 Mn MP by h square power 3 by 2. So that is a constant. In fact, you can also write Ni here as root A naught T power 3 by 2 e power minus Eg by 2 kT. Like this also you can write, where this is a constant, okay, independent of temperature. These parameters are independent of temperature. So as temperature increases more and more, Ni value increases more and more as per this. And mobility of semiconductor depends on temperature like this. Mu is proportional to T power minus m. T is the temperature. M is a constant, 2.5 for electrons and 2.7 for holes. This is in silicon, and it is 1.33 for electrons and 2.66 for holes. This is in germanium. So these are standard values. Please remember this. At very high temperature, the extrinsic semiconductor acts as intrinsic semiconductor. Yes, Hemant, yes. You know, as temperature keep on increases, Fermi level moves closer and closer to the center. So if it is coming closer and closer, means it is becoming intrinsic semiconductor. If the temperature is sufficient enough that Fermi level moves very close to center, the semiconductor is almost behaving like an insulator. And then conductivity. So conductivity at T2 temperature is sigma 2, conductivity at T1 temperature is sigma 1. So sigma 2 is obviously greater than sigma 1. So conductivity increases with temperature. How much? Sigma 2 is sigma 1 into 1 plus alpha into T2 minus T1, where alpha is temperature coefficient. Is a constant and temperature coefficient it is called as. Energy gap, very important. As temperature increases, energy gap of the semiconductor decreases. As energy gap decreases, electron hole pairs will be more. That's why Ni is more. As temperature increases, Ni increases more. Why? Because energy gap decreases. So how the relation? Energy gap at any temperature is equal to energy gap at 0 Kelvin minus beta T. T is the temperature, beta is a constant. How much it is? 3.6 into 10 power minus 4 for silicon, 2.23 into 10 power minus 4 for germanium. So 1.21 minus beta, silicon beta into 300, if you substitute, you must get 1.21. Similarly for germanium also. So at any temperature, you can find the energy gap from this equation. Okay, because sometimes it may be asked that some semiconductor parameter at 400 Kelvin. Generally, we deal with 300 Kelvin. At room temperature, we discuss generally. But if it is required, we may go to 400 Kelvin also if it is asked. Then in that case, we have to find what is the energy gap at that temperature. Another two important currents we need to talk about. In semiconductor, there are two currents possible. One is called drift current, another is called diffusion current. So what is the difference? Drift current is very simple, like normally whatever the current in conductors we are talking about is the same type of current. It is due to the drifting of charge carriers. Drifting of charge carriers. The charge carriers can be electrons, can be holes. And this drift current happens in the presence of electric field. If you apply some electric field, if drifting of electrons is happening in the direction opposite to the electric field, if it is electrons, right? The drifting of electrons happens in opposite to the electric field and results a current. That current is called as drift current. So drift current is the electric current due to the motion of charge carriers under the influence of an external electric field. This is important. Under the presence of electric field, if current happens, that current is called as drift current. That current can be due to electrons, can be due to holes, or it can be due to both also. But if there is an electric field, then that current is called as drift current. Okay. So now another current is called as, this is what an example with a beautiful animation. This is the semiconductor. Let's say it is N-type semiconductor. So these all orange color balls are like electrons. They are randomly moving. when there is no electric field is off, right? So this box is n-type semiconductor box, and white color balls are holes, very less in number of holes. But once you apply some electric field, you see here, when electric field is on, all electrons are moving in a particular direction. See, all electrons are moving from here to here. Holes are moving from here to here. They are all moving in a particular direction because the electric field is in this direction. So under the electric field, charge carriers are drifting from one side to other side. This type of current is called as drift current. Is this animation good, guys? Gives you clarity? Similarly, there is another current. Yeah, under the electric field, how the energy band of a semiconductor is. So this is also very important. Energy band diagram for n-type semiconductor. When there is no electric field, when E is equal to 0, this is the energy band diagram, right? N-type semiconductor, Fermi level is close to conduction band, electrons are in a conduction band, like that. But when electric field is not equal to 0, when electric field is applied, there is a bend in electric field, bend in energy bands happens. Yes, Hemant. Okay, a bend in energy levels happens when there is an electric field. Why? Electric field is in this direction. Suppose if this is the n-type semiconductor, okay, electric field is in this direction. This is electric field. Electric field is in this direction means this side is positive and this side is negative. So then only electric field is from left to right. If that is the case, the electrons at this end, at the right side of this my hand, the electrons energy will be higher because it is connected to the negative terminal of the battery. Electrons energy will be higher at this end. That's why the energy is higher here. Electrons energy is higher and this side it is lower. That's why shift in energy bands happens. That is why electrons can easily drift from this to this. Electrons are drifting, that's the reason. So if you find energy band is shifted like this, that means the semiconductor is applied with some electric field. There is some electric field across it. So there must be drift happening. If the energy band you see is like flat like this, that means there is no electric field across it and there is no drift happening. Understood? This is very, very important. Note a point. Suppose if the electric field is in this direction, then the shift in energy levels happens like this. So electrons will have more energy here and they'll drift like this. Okay? That depends how you apply. So the another type of current possible is diffusion current, and it happens when electric field is not there also. Even when there is no electric field, diffusion current may happen provided there is a concentration gradient. Electrons or holes, charge carriers will move from higher concentration region to lower concentration region, resulting a current called as diffusion current. And that process moving from higher concentration to lower concentration is called as diffusion, and that current is called as diffusion current. Is it clear? So like this. So these are randomly moving, for example, and when electric field is not there. Of course, this is drift current only. This is drift current for p-type I am showing. So far earlier we have seen for n-type, now it is shown for p-type. Of course, electrons are randomly moving when electric field is off. Now when electric field is on, see, holes are moving along the direction of electric field. So this is drift current, as I already shown you. Drift current equations as already we have seen earlier also, the same equations here also. Due to electrons is this, due to hole size. Suppose if both electrons and holes are diffusing, the total current will be sum of these two currents. It will be sum of these two currents. Then diffusion current. Diffusion current, as I just told you, happens because of concentration gradient. If there is a concentration gradient, then only diffusion current happens. As the flow of charge carriers within the semiconductor travels from higher concentration region to lower concentration region. How? Like this. See? This is for p-type and this is for n-type. See, initially more holes are here, that's why they are moving from here to here. More electrons here, they are moving here. They are diffusing. This process is called as diffusion. So electrons and holes are diffusing, right? And the diffusion current density can be defined like this: Jn is equal to Q dn by dx. This is what called as concentration gradient. Concentration gradient. And this is also concentration gradient of holes. This is concentration gradient of electrons. dN is diffusion coefficient. dP is also diffusion coefficient for electrons and holes respectively. It is a constant. Okay. And for different semiconductors, its value is different. And I have given in the tabular form in the beginning the values of silicon, values of dN and dP for silicon, germanium, etc. Remember, if there is a concentration gradient, then only diffusion. If there is an electric field, then only drift. If both concentration gradient and electric field both are there, then both current happens simultaneously. Okay. Under equilibrium means, Hemant, equilibrium is the state where net current is 0. Equilibrium is the state where net current is 0. Chinmay Rai, when electron flowing higher concentration to lower concentration is called as diffusion current. Yes, not only electrons, Chinmay, it can be for holes also. If the charge carriers are moving from higher concentration to lower concentration, the current is this current, diffusion current. Please make a note, here there should be a negative sign, guys. Here there should be a negative sign. Because of direction of the current, there should be a negative sign. There is a typo error there. Energy band diagram for concentration gradient. If concentration gradient for p-type semiconductor, suppose if concentration of holes is more here, that means Fermi level should be close to that. See here, Fermi level is far here. Far means less holes at this end. Very near means more holes near that end. That is why holes are moving from here to here. Similarly, n-type semiconductor, Fermi level is very close here and not that close here. That means the number of electrons here is less, the number of electrons here is more. But see, the band bending is not there here. See, the bands are flat here. The bands are flat. Bands are flat. That means there is no electric field. But the Fermi level is bent. That means diffusion is there. Understood? Concentration gradient is there. If electric Fermi level is if the energy bands are bent, then what happens? There is an electric field in that case. If energy band is flat, that means there is no electric field. Okay. Carrier lifetime. Lifetime is nothing but the time of a charge carrier before recombination and after generation is called as carrier lifetime. Is defined as average lifetime it takes before recombination. Okay, and how much it is? It is root d tau. L is equal to root d tau. Tau is called the carrier lifetime, and d is diffusion coefficient, as I just told you. L is the diffusion length. What is diffusion length? Lifetime is how much time, it is denoted with tau. Lifetime is denoted with tau. How much is the charge carrier exist before recombination and after generation? Diffusion length is the average distance covered by the charge carrier before recombination and after generation. So, the relation between lifetime and this diffusion length is L is equal to root d tau. Tau is lifetime, L is diffusion length, d is diffusion constant. Another relation we have like Einstein relation is mass action law is Einstein relation, which is nothing but d by mu is equal to Vt. D by mu is equal to Kt by Q, or it is equal to Vt. So, it can be applied for electrons or it can be applied for holes. So, this is Einstein relation. Yeah, then the Hall effect, what is Hall effect states you is, if there is a semiconductor, like this is a semiconductor, let's say for example this is n-type semiconductor. Okay, if a semiconductor is applied with some current, okay, applied with some electric field where current is flowing, and applied with a magnetic field also perpendicular to the current direction, then there will be a voltage induced across the semiconductor, and that voltage induced is called as Hall voltage. It is proposed by Hall, scientist Hall, that is why on his name it is Hall effect. When a current carrying conductor placed in a transverse magnetic field B. So, if I say there is a current flowing like this, let us say this is a current flowing I, and if there is a magnetic field, current is flowing in x direction. If there is a magnetic field in this direction, for example, this is the B. So B is in Z direction. Magnetic field is in Z direction. An electric field E is induced in the direction perpendicular to both I and B. So there will be an electric field induced in this direction, in this direction, in this direction there is an electric field in this direction. Induced electric field, we call it as EH. So because of that, there will be some potential across this semiconductor, and that potential we call it as VH. We call this potential as VH. How much is that VH? Is B into I, this VH is equal to Hall potential, we call it as B into I by Qn into W. Similarly, RH is called as Hall coefficient. It is a constant Hall coefficient whose value equal to 1 by Qn can be given as, it is VH, it is not VA, it is VH. VH into W by BA. It is from this equation only. We can find from this Hall effect, we can find from this experiment applying a semiconductor with a current perpendicular to magnetic field, we can find how much is the mobility of the charge carriers inside. So conductivity and RH we can find from this, and we can find the mobility as well. You can even find the conductivity. That is the benefit of using Hall effect, or application of Hall effect in fact. I have listed down this. Hall effect, what is the significance of this? We can identify whether semiconductor is N-type or P-type based on the polarity of the Hall voltage. For N-type semiconductor, Hall voltage is positive, for P-type it is negative. If you find by this experiment if Hall voltage is positive, it is N-type semiconductor. It is used to determine Hall voltage, Hall current, Hall coefficient and conductivity. We can find all these parameters. We can measure carrier concentration, number of charge carriers, how many. We can measure mobility of the charge carrier, just now I told you. We can measure even magnetic flux density, how much is the B. So by measuring how much is V, we can find how much is the B from the equation VH is equal to BI by Qn into W. Okay. So this is the application of Hall effect. And the last topic to discuss under semiconductors is continuity equation. So continuity equation can be applied in different fields, like in electromagnetics also we can apply, semiconductors also we can apply. I'm not explaining detail because it takes another 45 minutes time if I want to explain how this is and all. But these continuity equations can be used in deriving diode current equation, etc., in further topics. But just take the note of these equations. What is continuity equation? This is the continuity equation, dou n by dou t is equal to 1 by q dou jn by dou x plus gn minus rn. This is for N-type semiconductor and this is for P-type semiconductor. Okay. Expansion form of this, expansion for writing this Jn, what is Jn? We know already conductivity equation. So expanding this will be the N-type semiconductor and this is for P-type semiconductor. Okay. So this is continuity equation. I just very shortly I gave you the equations. Of course, it can be explained as per the time constraint because semiconductor only we have taken almost 2 hours. Next topic also to be taken. Sanjay sir is going to come and take this next topic. But before that, let me take another 5 minutes. By showing you a few more topics and some numericals. Okay. Direct and indirect band gap semiconductors. So just brief, I'll tell you what is direct and what is indirect band gap semiconductor. This is not the energy band diagram actually, you know, it is energy. This is a graph between energy and K. Momentum it is, similar to momentum it is, not exactly even momentum it is. So this is the graph between energy E and momentum is denoted with K. What is direct band gap semiconductor is, this is EC actually, the lowest energy of this is EC, the highest energy of this is EV. Don't get confused with the energy band diagram. Sir, why in energy band diagram it is flat and why it is curvature here? So it is not energy band diagram. So it is the energy versus K graph, EK diagram we call it as, okay. It is something different to explain. But remember, the lowest energy of the electrons in the conduction band is this. If this electron to move from here to the valence band, directly it can move from here to here, where there is no momentum required for the electrons to move from conduction band to valence band. Such semiconductors are called as direct band gap semiconductors. Okay, example gallium arsenide is a direct band gap semiconductor, gallium phosphide, etc. So the electron from conduction band to valence band directly moves, it doesn't need a momentum. Whereas in indirect band gap semiconductor, so this is ECE, as we just said, is ECE, and the electron here cannot directly come to occupy this valence band here, because along with losing the energy, this also have to have some momentum to reach to the valence band here. So it has to lose energy and it has to have some momentum, and then it has to come to valence band. Such type of semiconductors where electron needs momentum as well as losing energy to come to conduction band to valence band is indirect band gap semiconductor, like silicon, germanium are indirect band gap semiconductors. To make this process faster, we add some impurities, imperfections in the semiconductors, or the charge carriers will use the imperfections to have that momentum and move from conduction band to valence band. That's what we call it as traps. We add some traps to help this process happen faster. Okay. How can we define with respect to material properties, sir? What is that? I didn't understand. What we have to define with respect to material property? How can we define with respect to material completely? What we have to define, Monica? What we have to define? Yeah, momentum versus energy graph it is. This is indirect band gap semiconductor. Okay. So let's see some numericals. I'll give you some homeworks and some solution also here. After discussing these many topics, let's refresh and apply in terms of questions. The primary reason for widespread use of silicon semiconductor device technology is, this is asked in GATE 2005 for 1 mark question, guys. It is a very direct question. Why silicon is preferred over germanium or any other semiconductors? Is availability. Silicon is availability, abundance of availability. Option A. Larger band gap of silicon compared to germanium. It is also reason, yes, in fact it is also reason, but this is the better answer. Favorable properties of silicon dioxide, no. Lower melting point, not all these. So this is the best first point, and this is also correct in fact. Energy gap is larger for silicon than germanium. That is why leakage current is very less there. Yeah, in fact B is also correct, but A is more appropriate answer. So better to go with A. The band gap of silicon at 300 Kelvin is, I think you all must know, it is 1.1 electron volts, right? Come on, next question. Let's see some numericals. The resistivity of uniformly doped n-type silicon is 0.5. Resistivity is denoted with rho. It is given 0.5. If electron mobility is 1250, the charge of an electron is 1.6 into 10 power minus 19. The donor impurity concentration Nd of the sample is. Resistivity is always equal to 1 by conductivity of what semiconductor it is, n-type. So conductivity. So I can say 1 by conductivity of semiconductor is, n-type semiconductor is Q into N into mu N. So 0.5 is equal to 1 by Q is known, 1.6 into 10 power minus 19 into N is nothing but Nd. How many are the electrons? Equal to the donor concentration. Into mu N is given 1250. So simplify for Nd, you will get it. So how much is Nd is the answer. Okay. Perfect, Ravi Shankar. That should be the correct answer. Done, guys? Like this you can calculate. Take some more questions like this. A silicon sample A is doped with this of boron. Sample B is also GATE question asked in 2005. Please take it as homework. You can do this after these discussions. Nothing out of the discussion happened. I just want to show you some of the previous questions that, you know, whatever the questions coming in the GATE is not beyond our discussions. So if you are thorough with the discussions and the topics what we covered so far, what we revised so far, that is more than sufficient to answer any question from the semiconductors. Okay. So I think answer is B for this, guys. B or A it is. I'm not sure. We just need to do. So asked is to find the ratio of electron to hole mobility is 3. The ratio of conductivity of the sample A to B. Conductivity of sample A, conductivity of sample B is what? Conductivity of A is what? Boron. Boron means Q into P into mu P by conductivity of A is N type, it is Q into N into mu N. Doping is same for both, so this and this can be gone, so it is equal to mu P by mu N is the answer. But ratio of electron to hole is 3, so hole to electron is 1 by 3. So 1 by 3 is the answer. 1 by 3 is the answer, guys. Take this as homework. Take this as homework. You just need to find how many are the electrons and how many are the holes. Okay. This also has homework. I am giving all these questions as homework to you. You can do these questions. As I told you, if you don't get, please ask me. This is my email ID. You can ask me at any time. Okay. So you can take the screenshot and you can ask the questions. If you don't get the answer, please try to do it first. If you don't get, then only please ask me. So these all questions, I'll share you the PDF also if you want. Please work on this. These all questions can be answered with the topics what we discuss. Okay. So nothing beyond the questions. So this is asked in 2020 ISRO exam. So sometimes some questions are also good in ISRO. Maybe similar to GATE exam. So cross coupling also sometimes happens. So you must know some questions from other competitive exams as well. So this is on current density equation. So this is depending on diffusion current density equation. So that's all guys from my side. Now give me just 2 minutes time. Sanjay Rathi sir is going to join with us. I'll just inform him that he will join, and thank you very much for joining this session. And you know, write the mock test guys, subject wise test also, that gives you a lot of confidence for you, and perfection and you know, accuracy, speed, all those things can be improved by writing more and more exams. So keep doing that. And these are all available on our app. You can practice for your this one, but don't forget to like and share. So keep sharing it. So thank you all guys. Thanks for joining, and keep sharing it to other students. Let Sanjay sir join this session. Shall I call him or he's available? I think he must be available. Let me check with him once.
Oh no. Hello, is it audible? Sorry. Yes. Very good evening and welcome to the BYJU'S exam prep. How are you guys? I think now sound quality, picture quality, everything is fine. Yes, please. Everyone, very good evening and welcome to the BYJU'S exam prep, the most comprehensive app for all exams. How are you guys? Everything is fine. Sound quality, picture quality, everything is fine. So please share the link of this session, like the session and subscribe our channel. Already MN sir completed what semiconductor physics, that is one of the most important topic for coming GATE 2023. Okay, now I am going to cover two more important topic, that is what PN junction and BJT. And on Tuesday we are going to cover what remaining topic, that is MOSFET, special diode, and what MOS capacitor, that is CV characteristics. Okay guys, very good evening everyone, very good evening. Now this is a GATE 2023 Maha Marathon class EDC part 1, right? I am going to take. Then second one, that is my introduction. First of all, let me know that everything is fine now. Yes, Ravi Teja, Brahmanand, how are you? Navneet, Hemant Krishna, Zanani, Sonali. The number of students are here. Now आप देखते हैं जरा, this is my small introduction. Myself Sanjay Rathi. I am having around 21 plus years of teaching experience. And I have qualified and selected for engineering services exam. These are my ranks: AIR 16 in ECE 2005 and AIR 21 in ECE 2008. I have mentored more than 1 lakh students for these competitive exams. Now, this is the Maha Marathon, right? There will be daily classes from 10 AM to 2 PM and then what? 4 PM to 8 PM. So guys, join, subscribe our channel, and definitely it will help you. So it is a complete revision series for you. Subscribe our channel now in just 12 days. In just what? 12 days. Quick revision, each and every important topic. Then this is very important workshop for you, how to ace the GATE 2024 with college or what? Job. By Dheeraj Sardana sir, MTech from NIT Bhopal, 11 plus years of teaching experience, and ask your junior to join this session. So please register yourself on our app, that is what BYJU'S exam prep, or on our what? Official website. Please note the time, 10th Jan at 7:30 PM. Now guys, two important topics. First one is what? PN junction, and second one is BJT. Okay, no doubt. In analog, again we have one topic, that is what? BJT. But in analog, what is the what is in syllabus? Biasing and stabilization of BJT, amplifiers by using BJT, right? Cell bias circuit, fixed bias circuit, collector based bias circuit, multi-stage amplifier, feedback amplifiers, and so on. Those are the applications of BJT, bipolar junction transistor. But here we will get the idea about the junctions, right? What about the PNP transistor? What about the NPN transistors, right? Emitter injection efficiency, characteristics of what? Common emitter, common collector, and common base. You will get the idea about what? Early effect or base width modulation. And before that, you will get the idea about what? PN junction. So in this session, we will try to cover each and every aspect of what PN junction means. When the PN junction is reverse bias, then what about the capacitance? That is called transition capacitance or depletion capacitance. How we are going to calculate the depletion capacitance? Then when the junction is forward bias, what is the equation of the current, right? And what is the effect of the temperature on the voltage across the diode when the diode is forward biased, and how to calculate the current, whether it is diffusion current or what? Drift current. What are the important formula with all numericals? Okay guys, so this is the important one. So first of all, I am going to start with what? PN junction. First of all, I will start with what? PN junction, and after that we will cover what? BJT, that is the bipolar junction transistor. Okay, then simply what is the PN junction? Tell me. Everyone in comments box, please give me the comments. What do you mean by the PN junction and which topics are important? Definitely I will explain each and everything, but please let me know that you have any idea about that. Yes, Hemant Krishna, Ravi Teja, Navneet, and other students. Right. And ask your friend to join the session now and like the session. Okay. Then just in a PN junction, get the basic idea about that. This is the PN junction. We are using the single semiconductor bar, and here we are giving Na type doping, and here we are giving Nd type doping. Now you have idea about drift current and diffusion current. Means when we are giving the Na doping, it will become negative ions, that is called acceptor ions. It will become acceptor ions. It will create what? Holes. And that is okay. It will donate one electron, and that's why this will become N type. It will accept one electron, that's why it will become negative ions, and it will create what? Holes. Since in this region the concentration of hole is very greater than concentration of electron, and that's why it is called P type. Here the concentration of hole is less than what? Concentration of electron, or we can say the concentration of electron is greater than concentration of hole. Okay, right? So that is what P is less than N. Here the electron is minority carrier. According to mass action law, the concentration of electron is given by Ni square by what? P, and P is nearly equal to what? Na. These two formula are very, very important. Here the minority carrier is holes, that is given by P and naught. Ni square by what? N, and what is N? Nearly equal to Nd. That is donor concentration on what? N side. So this is the P side and that is N side, and that is called metallurgical boundary between P and N type. This is a metallurgical boundary. It is not a physical boundary, it is a metallurgical boundary. Means ऐसा नहीं है कि P type लिया और N type लिया और फेविकॉल का जोड़ लगाकर connect कर दिया. Right? That is not the case. We are simply taking one single semiconductor bar. Here we are giving Na doping, here we are giving Nd doping, right? And then this will become P type and that will become what? N type. Now, remember one thing, because the concentration is very, very, very high. The concentration of P is very high in this region and this is very low in this region. Therefore, there is a concentration gradient. Concentration gradient. This is the P in P side and P and naught in N side. Very high. Therefore, there is a concentration gradient. This is called concentration gradient. Now, when there is a concentration gradient, the hole will move from higher concentration to lower concentration. When the hole move from higher concentration to lower concentration, then definitely there will be diffusion current. There will be the diffusion current. Then, when there is a diffusion current, at the same time, there will be the concentration gradient in opposite direction, because the concentration of electron in this region is very, very high as compared to this. Then we can say N is very, very greater than N in P region. Again, there will be the diffusion current because of electron, because there is concentration gradient. That is called concentration gradient of electron. Right? So there are two concentration gradient, one because of hole and one because of what? Electron. Now, hole will move from this point to this point. Electron will move in the opposite direction. So what will be the current? That is the hole. And that is the direction of the electron. This is hole. This is electron. Now, the current will be in the direction of what? Hole. And that's why there is a two current, IP plus IN. IP plus IN in the same direction. So in a gate exam, they will ask you the direction. So normally, remember one thing, this is called positive X direction. When we are moving in this direction, this is called positive X direction. That will be the question. This is called positive X direction. Okay. So means the diffusion current is in what? Positive X direction. That is from P to N side. Right. Now, this bar is what? Open circuit. This bar is what? Simply open circuit. There is no battery involved in this bar. Once the bar is open circuit, means what will be the total current? The total current should be equal to what? 0. For current, for particular circuit, for flow of current, the circuit should be what? Closed. But it is an open circuit. In an open circuit bar, the current will be 0. So what will happen? There will be the drift current. Right? There must be drift current, so that drift current will oppose the diffusion current and total current will become 0. Now, to make this diffusion current 0, there will be one potential, that is called potential barrier or built-in voltage. Right? Simply. So that is represented by VBI. VBI, or what? Sometimes it is represented as V0. And why we are getting this? Because first of all, in this area, some hole will diffuse from this region to this region, and some electron will diffuse from N region to P region. N region to P region. And that's why this hole and electron will recombine. Once they will recombine, there will be uncovered acceptor ions in p side and uncovered acceptor ions in donor ions in n side. So this is called acceptor and donor ions. This is uncovered, that is uncovered. And what about the remaining? Remainings are covered. Covered means this is neutral. This is negative, this is positive, this is negative, this is positive, and this is positive. This electron, charge of electron is negative, negative, and that is positive plus negative, that is neutral, neutral, and this area is neutral. This area is neutral, right? And just before this recombination, the complete area was what? Neutral. This was the neutral, but this was the neutral. Then the hole will diffuse from p side to n side and electron will diffuse from n side to p side and they will recombine. And because of this recombination, we are having uncovered acceptor ions in this region and uncovered donor ion in this region. And that region is depleted of mobile charge carriers. Means in this region, there is no mobile charge carriers. No mobile charge carriers. Which are the mobile charge carriers? Which are the mobile charge carriers? Electron and what? Holes are called mobile charge carriers. Electron is represented by this and hole is represented by this. It is negative charge carrier. It is a positive charge carrier. And what is the charge of the electron? 1.6 into 10 raised to power minus 19 coulomb, as I told you in just first session. Okay. Immobile, and these are called immobile charge carriers. These are the acceptor ions. This is the acceptor ion, and that is called donor ions. Acceptor ions and what? Donor ions. So these are called what? Immobile charge carriers. Normal. So in a depletion region, normally there is no mobile charge carriers, only immobile charge carrier exist. These are uncovered, and that's why they will develop an electric field in this direction. If this is the plus charge, it is the minus charge, then what is the direction of the electric field? From positive to negative. And because of this electric field, it will exert force on what? Electron as well as holes. So what is the force in case of hole? The force is given by QE. Means in the direction of what? Electric field. Means it will exert the force on holes in this direction, in negative x direction. What is the force on the hole electron? Minus QE. Means it will exert the force on electron in positive x direction. Positive x direction. So very, very simple. Initially, because of the concentration gradient, hole try to move from higher concentration to lower concentration. Means what about the diffusion here? Because of diffusion, hole are trying to moving from p side to n side, that is in positive x direction. And what about the force? In negative x direction. So that will stop the flow of holes. Similarly, electron try to move from n side to p side, that is called negative x direction. And what about this force? Because of this depletion region, it is in positive x direction. It will stop the flow of electron, that is diffusion, right? So under equilibrium, what about the flow? Zero. So what about the current? Zero. So in open circuit bar, the current will be what? Zero. But we are saying that there is a two currents. One is called drift current and another one is called what? Diffusion current. Drift plus diffusion is equal to what? Zero, right? No doubt. For drift current, there should be what? Electric field. And for drift current, there's electric field. Then for electric field, there should be what? Voltage. And that is called built-in potential. And for diffusion current, what is required? Concentration gradient. So both are present here. Concentration gradient is present. Electric field is present. Potential is present. And that's why we can say, what is the built-in potential? Vt log of Na Nd by Ni square. That is the important formula. Vt log of Na Nd by Ni square. When Na is the concentration of acceptor impurity, Nd is the concentration of donor impurity, Ni is the intrinsic carrier concentration, and Vt is called volt equivalent of temperature. And what is the value? In previous class already sir have discussed Kt by Q. Kt is called Boltzmann constant, Q is the charge, T is the temperature in degree Kelvin, and that is we are getting the T by 11,600 volt. And what is this? At 300 degree Kelvin, Vt, we are getting 0.0259 volt, or it is nearly equal to 26 millivolt we are using. Or if in a gate exam normally the temperature is given at 298 degree Kelvin or 25 degree centigrade, so Vt will become 0.025 volt or 25 millivolt. 25 millivolt. You can use these two value. If the temperature is given as 27 degrees centigrade, then use this value. If the temperature is given as 25 degrees centigrade, then this value. Okay. So this is called volt equivalent of temperature. Right. Remember one thing. Now these days they will ask, find the built-in potential at what 45 degrees centigrade or what 50 degrees centigrade. They are increasing the temperature. If they are increasing the temperature, then first of all find the value of the Vt by using this formula. Right? No doubt at the same time the intrinsic carrier concentration will also change. Already sir have given you the formula for intrinsic carrier concentration. Right? If the temperature will change, what about the intrinsic carrier concentration will increase? So normally students are thinking that sir, if the temperature increases, V0 increases. If the temperature increases, Vt increases. Vt increases, therefore V0 increases. No problem. It is directly proportional to Vt. V0 is directly proportional to Vt. And that's why when I am increasing the temperature, Vt will increase. Vt will increase means V0 will increase. But what about the Ni? So temperature increases, then intrinsic carrier concentration increases. So what about the N square? Ni square, it is also increases. And because of this, V0 will decrease because it is in denominator. Log of this value will decrease. So what about the overall effect? Tell me. What about the overall effect on V0? Decreases or increases? Because of one factor, it will increase. Because of this factor, it will decrease. So ultimately, when we are increasing the temperature, the built-in potential will what? Decrease. Built-in potential will decrease. Good. Built-in potential will decrease. Yes, Surya, Karthik, Hemant, and your answer is correct. With what? What is the effect of the temperature? We have to check two values, Vt as well as what? Ni square. So they will give you the temperature at different temperatures. So please read question carefully. That is first important instruction in every competitive exams, in every exam. Read questions carefully, read instructions carefully. Okay. Then, so that is one thing. Now, depletion layer established on both the sides of the junction, already we have discussed. Barrier potential developed across the junction, already we have discussed. Then formation of the junction and diffusion capacitance. Yes, there are two types of capacitance. One is called what? Depletion capacitance or transition capacitance. Another capacitance is called diffusion capacitance. Transition capacitance. Number of questions on this topic. Transition capacitance. Second one is what? Diffusion capacitance. Diffusion capacitance. Normally we are getting question on what? Transition capacitance. Transition capacitance means when the junction is reverse biased, or diffusion capacitance means when the junction is what? Forward biased. But tell me, why we are getting the capacitance? Why we are getting the capacitance? Because when we are making the junction forward bias or reverse bias, there is change in the charge. And what is the capacitance? Change in charge because of change in voltage. When there is a change in charge because of the change in voltage, definitely there will be capacitance. definitely there will be capacitance. So one by one we will try to understand what is the transition capacitance and what is the diffusion capacitance. Normally questions on these two topic, when the diode is forward bias or when the diode is reverse bias. Okay. Or in analog, that is the application of the diode. Application of the diode means what? Rectifier, filter, clipper, clamper, right? Voltage doubler. So already sir covered all those topics, right? And what number of standard circuit on diode, voltage regulator. These are the application of the diode. Okay. We have to understand the internal constructions of the diode, and what about the transition and diffusion capacitance, and what is the varactor diode here. Now, so first of all, what is the depletion layer? Try to understand. Depletion layer is created due to the diffusion of the majority carrier across the junction. Already I have given hole will diffuse in N side and will diffuse in the P side. They will recombine and the diffusion layer is created. Second, in this region, the thermopile charge carriers are 0. That means mobile charge carriers are 0. That is the important point. Depletion layer consists of a large number of ions and what? Covalent bonds. Large number of ions mean acceptor ions and donor ions, as well as what? Covalent bonds. Depletion layer opposes the majority carrier in crossing the junction. Yes, it will stop the diffusion of majority carrier from P side to what? N side, and from N side to what? P side. That is the purpose of depletion layer. They will ask that there may be the question, MSQ type question. Okay. Then this is also called depletion region, is also called space charge region or transition region. These are the name. Here we are having the negative ions on the P side. Remember that. Immobile charge carriers. Here we are having the positive ions, that is called donor ions. This is the negative charge area, positive charge area. This area is neutral. This area is neutral. Space charge region. What is the direction of the electric field? From positive to negative. That is the diffusion force on the electron. That is the electric field force on the electron. That is the diffusion force on the holes. This electric field will oppose the diffusion of the holes. So this diagram is very, very important one. Already I have explained what is the direction. So there now they will ask questions on what? Directions. Whether it is a positive x direction or what? Negative x direction. So by default, if nothing is given, remember, this is the positive x direction. Positive x direction. According to this, we can decide whether it is a positive direction or what? Negative direction. If it is in the same direction, means value is positive. If it is in opposite direction, then we can say it is what? Negative value. Negative value. Right? Number of times they will ask the question with what sign? Whether it is a positive value or what? Negative value. Okay. Then, next thing. Any doubt? Up to this point, any doubt you can ask? Yes, Surya, Karthik, Hemant, anyone, any doubt? Tell me. Yes, please. Now, next thing. This is a space charge region, already I have given. Now we will solve some questions on that. Please give me the answer. A very, very basic questions on this topic. Then I will cover what? Transition capacitance. First of all, in a uniformly doped abrupt PN junction, the doping level of N side is 4 times the doping level of P side. The ratio of the depletion layer width of N side versus the P side is. Is there is any relation between the doping level and the depletion layer? Is there is any relation? Yes. Means if this is given, right, like this is the P side and that is the N side, the uniformly doped abrupt PN junction. Abrupt means what? First of all, what is the meaning of this abrupt PN junction? Abrupt PN junction means we are giving the uniform doping in P region. Uniform means we are giving the acceptor doping here, that is uniform. The concentration is uniform throughout the P side, right? Similarly, here we are giving the uniform doping. Some students are confused with this. So remember that uniform doping means here we are giving the constant value, ND type, right? And it will create electrons. Okay, that is the uniform doping. But what about the concentration of hole here? The concentration of hole is Na, that is very, very high. And what is the concentration of hole here? This is Ni square by what? Nd. Very low. Then this is called abrupt junction. What is the meaning of this abrupt junction? Like this is the concentration. On y-axis we are giving the concentration. At this point the concentration is very high. At this point the concentration is very high. Suddenly the concentration will reduce. Suddenly the concentration will reduce. What is this concentration? From this point to this point it is Pn naught. Pn. P is equal to Na. And suddenly it will fall Pn naught. This is very small. This is called step grading. Right? Step graded junction or abrupt junction. Step graded junction or what? Abrupt junction. Right? Suddenly it will decrease. Okay, so this is called step. But what about the concentration in this region? Uniform. What about the concentration of electron in this region? Uniform. But suddenly it will fall. So this is called abrupt junction or step graded junction. When the concentration decreases like this, like this is the P, here it is the P, here it is the P2. From P1 to P2 it decreases linearly. Then it is called linearly graded junction. Linearly graded junction. Okay. So these are the 2 points. Okay. Then if that is it is an abrupt junction, always remember there will be the depletion width. There will be the depletion width in N side and P side. This is called depletion width. This is called depletion width on N side. This is called depletion width on P side. It is represented by Wp and Wn. Here we are getting the acceptor ions. Here we are getting the donor ions. Right? Here we are giving the Nd doping. Here we are giving Na doping. Remember, it is inversely proportional. Depletion width is inversely proportional to what? Doping concentration. Means more will be the doping, less will be the depletion layer. So what is the formula? Na into Wp is equal to what? Nd into Wn. That is the standard formula. Na into Wp is equal to Nd into W, and we have to use. Okay, so what is the answer for this question? In a uniformly doped abrupt PN junction, the doping level of the N side is 4 times the doping level of P side. Means Nd is 4 times as compared to what? Na. The ratio of the depletion layer width of the N side versus P side. Always read question carefully. N side versus P side. Means already I have given you the formula. Na into Wp is equal to what? Nd into Wn. You have to find Wn by Wp. So Wn by Wp is equal to what? Na by Nd. Inversely proportional to that. And what is the Na? Nd is equal to what? 4Na. Right? So Nd is equal to 4Na. So Na divided by 4Na, that is 1 by 4, nothing but 0.25. 1.25. 0.25. 1 by 4. N side versus P side. Very easy question. Very, very easy, but very, very important one, because in a complicated question, first of all, we have to find this value. Okay then. Now, That is the first basic question on what depletion layer. Now the second one. So this is a abrupt junction. This formula is valid, and then this is called linearly graded junction. Now what is the answer for this question? Again, formula based question. Formula based question. Consider the uniformly doped. When we are using this word uniformly doped, number of students are confused. Sir, what is the meaning of this uniformly doped? It is whether it is a step graded or what linearly graded. Uniformly means what? Here it is uniform. In P side it is uniform and N side it is uniform, and suddenly it will reduce. So that is called uniformly doped. It means we can say step graded junction. Consider the uniformly doped gallium arsenide junction at T is equal to 300 degree Kelvin at a zero bias, means we are not applying any voltage. Only 20% of the total space charge region is to be in the P region. If suppose it is a total region, then the 20% region on the P side and remaining 80% on N side, depletion layer. This is the Wn and this is what? Wp. If the total depletion width is Wp plus Wn, then we can say Wp is only 20%, matlab 0.2 times of W. And what is the Wn? Wn will become 0.8 times of W. W is the total depletion width. The built-in potential barrier is 1.20. Built-in potential barrier is given as 1.20 volt. For the zero bias, we are not giving any voltage here. Determine the Na and Nd. Ni is given. What is the Ni for gallium arsenide? Remember, 1.8 into 10 raised to power 6 per centimeter cube. For silicon, you have idea about that, 1.5 into 10 raised to power 10. For germanium, it is 2.3 into 10 raised to power 13. Very high for germanium, than for silicon, and very low for what? Gallium arsenide, only 1.8 into 10 raised to power 6. Now, we have to find Na and Nd. There are two unknowns, Na and Nd. And now we have two equations. What are the two equations? First of all, what is the built-in potential? Built-in potential is given by Vt log of Na, Nd by what? Ni square. This is the first equation. Vt log of Na, Nd by Ni square. Then, because there are two unknowns, V0 is given, Vt. Temperature is given, so Vt we know 26 millivolt. Na, Nd by Ni square, Ni is also given, so that is the one equation. So what is the another equation? Another equation is Na into Wp is equal to what? Nd into Wn. So what is the Na into Wp? What is the Wp? Only 20% of total depletion width. What is this? 0.8 of what? Total depletion width. So total cancel, and now you are going to get the relation between Na and Nd. So what is the Na is equal to 4 times of Nd. Na is equal to what? 4 times of Nd. Now put here 4 times of Nd. So it will become 4 Nd square by Ni square, and you have Vt. You can take the inverse log, that is called anti-log, and you can find the value. Is it easy? Tell me. This question is easy for you? Yes, please. Then I'm giving you the hint, that is what? Vt will become, V0 will become, Vt log of 4 Nd square upon Ni square. 4 Nd square, Ni square, and then when I'm taking the anti-log, it will become V0 by Vt. Anti-log means e raised to power that V0 by Vt. That will become 4 Nd square by Ni square. Then you can find the value. This will become Nd is equal to Ni square e raised to power V0 by Vt divided by 4 root over that. Root over that value. Okay. Okay then. Yes, I am giving you that. This is the case. There are the, now I am going to explain you. Calculation is your part. Just I am giving the, this is the formula based question. Okay. So Ravi Shankar, try to understand. If it is given, consider the uniformly doped gallium arsenide. It doesn't matter whether it is gallium is given or gallium arsenide is given or germanium is given or silicon is given. They will mention, they will give you the data also. But sometimes if they are not providing you the data, then please try to revise the what standard value. These are called typical values. 1.8 into 10 raised to power 6, that is the Ni for gallium arsenide. Temperature it is given 300 degree Kelvin. Now at zero bias, only 20% of the total space charge width. This is the total space charge width from this point to this point. 20% on the P side and remaining 80% on the N side. Means on the P side the doping is very high. Doping is very greater than Nd. Depletion width here is only 0.2, here is only 0.8, means 4 times. So directly we can say Na is 4 times greater than what Nd, or otherwise from this formula you can find. Okay, this formula you can find. Once you will get the relation between Na and Nd, with the help of this formula you can find V0 is given in the question, Vt is given in the question, Na, Nd you have to find. Now tell me, easy guys, please watch and then give me the answer. 2 unknown, 2 equations. You can use virtual calculator only. Okay, tell me that is clear. Okay, so now next one. So this is one type of question here, very important concept, but right. The next one, for example, read this question. Step graded diode. What changed? Step graded. And in the previous question, what is asked? Yes, you can calculate. P. Rajesh, if it is the answer, yes, I think that is the correct one. Otherwise, check your calculation. Now, second, what is written in the previous question? Read. Consider the uniformly doped. What is the meaning of this uniformly doped? This side P side, this side N side, that is uniform in this region, that is uniform in this region, and abruptly there is a fall from higher side to lower side. This is an abrupt junction or step graded junction, same word. But in a next question, what is the word used? Step graded diode. Step graded means again suddenly there is a change in the concentration. Suddenly there is a fall in the concentration, and that is called step graded junction. Having Nd is equal to 500 times of Na. 500 times of Na means what about the Na? Very small, or Nd is very greater than what Na? With acceptor impurity to the extent of 2 into 10 to the power 8. What is the meaning of this 2.10 to the power 8? Means 2 part in 10 raised to power 8 of germanium atom, right? Or in a semiconductor physics you learn about that. 1 part in 10 raised to power 8, or 2 part in 10 raised to power 8, or 10 part in 10 raised to power 8, or 10 raised to power 6. Means we are giving 2 impurity atom per 10 to the power 8 germanium atom. 2 impurity atom per 10 to the power 8 germanium atom, and with impurity, with acceptor impurity, that is what? Na. Na it is given. Then tell me, total number of atoms of the germanium it is given. Vt is given. This is the value of Ni. Find its contact potential. Find its contact potential. Okay, 2 part in 10 raised to power 8. Okay, then to find its contact potential means very simple. Again, first of all, always write this formula. You have to find the Vt log of Na Nd by Ni square. This is the first one. Okay, you have to find this. That is given in the question. Now, what is the Vt? Temperature. What is the temperature given, or Vt is given? Directly Vt is given 26 millivolt. Okay, no problem. Now you have to find the value of Na and Nd. Nd is 500 times of Na. But what is Na then? 2 part in 10 raised to power 8. How many germanium atoms? 4.421 into 10 raised to power 22. So directly we can say Na is equal to 4.421 into 10 raised to power 22 divided by what? 10 to the power 8. लेकिन क्या बोला इसने? What is this? Is the when we are giving in 10 raised to power 8 we are adding 2. In 4.421 into 10 raised to power 22 we are adding how much? We can directly say 2 divided by 10 to the power 8 into what? 4.421 into 10 raised to power 22. So it should be multiplied with what? 2. It should be multiplied with what? 2. What is the answer? Then you will get the concentration of what, or value of what? Na. Value of Na. When I am multiplying it, this will become 248.8 into, this is divided by 10 to the power 8, 10 to the power 14. And that is the value of Na. Once you will get the value of Na, what is the Nd? 500 times of Na. Finished. Question now over. Okay. Any doubt? 500 times of Na. So this type of questions. So directly you have to find the built-in potential. Vt is given in the question. Na, Nd, it is given in the question. But what is the new in this question? That is new in this question. 2 into 10 raised to power 8. ऐसा dot लगा हुआ है. So this is the, what is the meaning? 2 part in 10 raised to power 8 of germanium atom. Or directly they will mention 2 part in 10 raised to power 8 germanium atom. That is the impurity concentration already. And in semiconductor physics, as you know, 1 part in 10 raised to power 8 is a normal doping, right? Or 1 part in 10 raised to power 6, that is 1 part in 10 raised to power 8 or 10 raised to power, this is called moderate doping. And 1 part in 10 raised to power 3, this is called very, very high doping. In which case we are using the very high doping. Give me the answer in the comments box. Everyone give me the answer in the comments box. In which case we are using, in which diode we are using the very, very high doping. That is 1 part in 10 raised to power what? 3. 1 part in 10 raised to power 3. So one student have given the answer, that is 0.347. Yes. So 1 part in 10 raised to power 3. This is very high doping. In normal diode or normal BJT we are using this much doping, right? 1 part in 10 raised to power 8 or 1 part in 10 raised to power 6. Okay. In between these two. Oh yes, we can say in general diode that is a highly doped P positive N junction, and second one is what? Tunnel diode. In tunnel diode again we are using very, very high doping, ECE diode or tunnel diode. Okay then. So in a special diodes we will cover all this. In special diodes we will cover all this topic. So please subscribe our channel so that you will get the notification about the session. Tuesday 4 p.m. Don't miss that session, because we are going to cover what? Complete MOSFET, MOS capacitor, and what? Special diodes. Special diode. All the special diodes, whether it is a LED or solar cell or what, that is tunnel diode and so on. Okay. All the diodes that is mentioned in your syllabus. Okay then. That is about this question. So I think directly now you can use the formula and you can find the value of V0. Now you have the value of Na, you have the value of Nd, Ni is given in the question, Vt is given in the question, then you can find the V0, built-in potential. Then next one. Okay, tell me what is the answer? Quickly, you can give the answer. Yes, we have Hemant Krishna tomorrow afternoon session. Oh, first of all, I will get the information and then I will inform you. Okay, Hemant. Okay then. The depletion layer across a P positive engine. When the word P positive is used, P positive means high doping, highly doped P region. Highly doped P region. So Na is very, very greater than what? Nd. Very, very greater than Nd. That it is called P positive N junction. So depletion layer across a P positive N junction. Always remember, depletion layer in P region into Na is equal to depletion layer in N region into what? Nd. So what is the depletion layer in P region? It is inversely proportional to Na. If we are increasing the Na, what about the WP? Decreases, inversely proportional, negligible. In P side it is what? Negligible. So definitely the mainly you are giving the equal in both the region. No. By why, if they are equal, depletion layer across P positive N junction. My dear students, this is the formula. You have to satisfy this formula. Okay, Ravi Shankar, not is clear, and that's why it is mostly in what N region or negligible in P region. More will be the doping, less will be the depletion layer. You have to satisfy this formula. You have to satisfy this formula. Within 10 seconds, you have to solve this type of questions. Now, this time they will give you MSQ. Which statements are correct? So that there may be one statement. There may be one statement. Okay. Okay, then next one. Mostly in the N region. Less will be the doping, more will be the depletion layer according to this formula. Okay, then next one. No, try to solve this question. At 300, I am giving you what is the importance of this point. What is the importance of these two formula? Then after that we will enter into what? Transition capacitance, depletion capacitance. Again we will solve some questions. Then we will enter into what? Next topic, that is what? Forward bias diode. Again we will solve some questions. Then I will give you the idea about the switching time. Switching time. What is the forward recovery time and reverse recovery time? Again we will solve some important numericals on that. Right? Then diffusion capacitance. Okay, and then we will enter into what? BJT. So first of all, try to solve this question. 300 degree Kelvin for a diode current of 1 milliampere. Certain germanium diode requires a forward bias of this much. Whereas a certain silicon diode requires a forward bias of 0.718 voltage. Under the condition stated above, the closest approximation of the ratio of the reverse saturation current in germanium diode to that in what? Silicon diode. Right. Now this question is what? Based on what? Equation for the current. Equation for the current. I is equal to I naught e raised to power V by eta Vt minus 1. That is called equation for the forward bias diode. What is given? For a diode current of 1 milliampere, certain germanium diode. Right. Now we will explain each and everything about this equation and then we will solve this question. If you have idea about that, then everyone try to give me the answer. Which answer is correct? Which answer is correct? Otherwise, first of all, I will give you the idea about this equation, then I will solve this question. In comments box, give me the answer. What is the answer for this question? We will check. Okay. Then, first of all, when we are dealing with the diode, already I have given what is the built-in potential, what about the depletion layer. Second topic is what? There are three reasons in which the diode works. First, zero bias. We are not giving any voltage, any external voltage. We are not applying any external voltage. Then there will be the built-in potential. Already we have solved one question on that. How to find the built-in potential when there is a zero bias. Already we have solved question. Second is what? Forward bias. When the diode is forward biased. So this is the symbol for the diode, right? And when it is given plus or minus, this is called forward bias diode. When the positive terminal voltage is greater than negative terminal voltage, we can say the diode is forward biased, or when the voltage across the diode is positive, we can say the diode is forward biased. Another one, if this is plus, then we are saying that the diode is what? Reverse bias. Diode is reverse bias. So when it is a forward bias, then what about the depletion layer? When it is a reverse bias, then what about the depletion layer? So we will discuss here one by one. One by one we are going to discuss here. First of all, this is the important topic when the diode is reverse bias. Reverse bias. So number of questions on this topic. Watch this diagram. Sometimes I am changing the orientation of diagram. Definitely it is going to confuse you. This is the P side and that is what N side. So sometimes they will give you the diagram like this. This is the P side, that is the N side. Be careful because it is connected to negative terminal. P side is connected to negative terminal. N side is connected to positive terminal. We can say this junction is what? Reverse bias. Now, I am giving you the simple diagram. Let. This is P side. It is connected with the negative terminal. It is connected with the positive terminal. It will attract holes. the negative will attract holes, and holes are moving away from the junction. Holes are moving away from the junction. Similarly, this positive terminal will attract electrons. So electrons are moving away from the junction. Holes are moving away from the junction. Therefore, depletion layer increases. Therefore, the depletion layer increases. Already it is up to this point. Now the depletion layer increases from this region to that region. Okay. So when we are making the junction reverse bias, definitely the depletion layer will increase. That is the widening of the depletion layer. Okay. Now which topics, when we are increasing the depletion layer, then definitely the immobile charge, concentration of the immobile charge carrier will increase. So there is a change in charge because of change in voltage, means there is a property of what? Capacitance, dq by dv, and that is called depletion capacitance. That is called depletion capacitance or transition capacitance. This is also called transition capacitance. Depletion or transition capacitance. So this is a very important topic when the diode is reverse biased by voltage VR. So what are the important formula related to that? First of all, always remember that transition capacitance, very simple, just like a parallel plate capacitor, it is given by epsilon S A by W. Sometimes this is a 1 mark question, they will directly ask what is the value of the capacitance. If the depletion layer is given, A is given, epsilon S is given, right? Directly transition capacitance, just like a parallel plate capacitor. But remember, epsilon S means epsilon R, epsilon naught. Epsilon R for S silicon, they will provide you the value, sometimes 11.7 or sometimes 12, they will give you the value. Epsilon naught, as you know, 8.854 into 10 raised to power minus 14 farad per centimeter. Normally we are using in centimeter, so that is the value of epsilon. A area they will provide in numerical, and W, that is the depletion width, total depletion width, Okay, that is the one type of question. Directly formula based question, you have to find what? Transition capacitance or depletion capacitance. Second one, you get transition, this is the first formula, transition capacitance, just like a parallel plate capacitor. Directly we are going to use this formula. Second, they will provide you how to find the capacitance, means VJ. This is another formula, that is called junction voltage, Qn by 2 epsilon S into W square. Right? Okay. Again, directly based, when the diode is reverse biased, VJ, Qn by 2 epsilon S into W square. Remember, where Vj is the junction potential. Right? Vj is equal to V0, built-in potential, plus Vr. Vr means voltage applied in reverse direction when the diode is reverse bias. When we are giving the voltage like this, you have to use this. This is called Vr. Or when the diode is forward bias, then Vj will become V0 minus Vf. For example, you have the idea about this Vf, then you have to use this formula for Vj, V0 minus Vf. N means 1 by N, that is given by 1 by Na plus 1 by Nd. 1 by Na plus 1 by Nd. Right? Remember this, 1 by Na plus 1 by Nd. Then, how to find N? If suppose the general formula for N, it will become Na Nd upon Na plus Nd. But always there is some special cases, Na is very greater than Nd. Then simply 1 by Na is negligible. N will become nearly equal to what? Nd. Second case, if the Na is very less than Nd, 1 by Nd is negligible as compared to 1 by Na, then N will become what? Na. Which one is smaller? The value of Na. Otherwise, if these two are comparable, then directly you have to find what? N. 1 by Na plus 1 by Nd, or Na Nd upon Na plus Nd. Is it clear? This point is clear? Sir, क्या हो गया? Another formula for depletion width. Yes, I am going to give you each and everything. Now, I think Vj is equal to Qn by 2 epsilon as W square. So what is the, first of all, what is the N? So already I have discussed N. Already I have given the value of the Vj, first thing. Second thing, Na. Third is epsilon S. Already we have discussed what is the epsilon S. Epsilon or epsilon naught. Already we have discussed. Then you, from this formula, you can find the value. If suppose the Q is constant, N is constant, 2 is constant, epsilon S is constant. So what about the depletion width? It is proportional to what? Root over Vj. Or we can say W is proportional to Vj raised to power 1 by 2. So what about the transition capacitance? Epsilon Sa by W. Since it is inversely proportional to W, we can say Ct is proportional to 1 by root over Vj. Inversely proportional to Vj, root over Vj, or we can say Ct is proportional to Vj raised to power minus 1 by 2. Vj raised to power minus 1 by 2. Number of times, same type of questions from the transition capacitance. Okay, this is the transition capacitance. Right. Second important thing, second one, how to find the electric field, right? When we are increasing the voltage in the reverse direction, definitely the depletion layer will increase, Wp will increase, Wn will increase, right? Once the depletion layer will increase, definitely there is a change in the electric field. So where we are going to find a maximum electric field? What is the magnitude? Where we are going to find a maximum magnitude of the electric field? And from that we can find what? Potential barrier also. So we will solve some numericals on that and you will get the idea about that particular thing. Ready to solve some questions? So this is about the reverse bias. So remember, always remember, what is the direction of the electric field? Already I have given. If this is the plus side, this is the minus side, that is the direction of the electric field. That is the direction of the electric field. And what is the direction of the electric field because of the applied voltage? Because this is because of the depletion layer. So what is the direction of the applied voltage? Again, it is in the same direction. That is in the same direction. Okay. Now, under ideal condition, in depletion layer, there will be no mobile charge carriers. But under practical condition, when we are increasing the temperature, new hole electron pair will generated in this region. When the new hole electron pair will generated in this region, in depletion region, everyone tell me what about, suppose the whole electron generated here, whole electron generated here, whole electron generated here. So what about the electron, right? Now the electron, under the influence of this electric field, hole will move in the direction of the electric field. That is the direction of the hole, right? That is thermally generated charge carriers in the depletion region will move from N side to P side. And what is the direction of the electron? Electron will move in the opposite direction. Hole will move from N side to P side, N to P side, from lower concentration to higher concentration. And electron will move from P side to N side, that is again lower concentration to higher concentration. And if it is moving from lower concentration to higher concentration, means definitely it is not what? Diffusion current. So what is this? It is what? It is a drift current. It is what? Drift current. From lower concentration to higher concentration, or that is the drift current is because of what? Minority charge carrier or thermally generated charge carrier. Since the drift current, it is proportional to what? Concentration. What is the formula for the drift current? J is equal to I by A, that is the drift current density, that is equal to nothing but sigma E. And what is the sigma? NQ mu N into E plus PQ mu P into E. Since the concentration of electron as well as concentration of hole is very less thermally generated charge carrier, and that's why this current from N side to P side is very small. This is a minority charge carrier concentration that is given by Ni square by what? Nd. And what about the Np naught? Np naught is given by Ni square by what? Na. Now, when I am putting this value, the I naught will become AQdP Ni square by Lp into Nd AQdN Ni square by Ln into Na. Okay, now you can take common, A common, Q common, Ni square common. So under bracket, A common, Q common, Ni square common. Under bracket it will become dP by Lp into donor concentration plus dN by Ln into an acceptor concentration. And that is the formula for what? Reverse saturation current. Remember, you are from EDC branch. You are from electronic devices and what? Circuit. Right? It is EDC. EDC is the very important subject for what? Electronics and telecommunication students. Na? So they will ask what is the value of the reverse saturation current, how to find the reverse saturation current, and so on. This is a very important one. Lp is called diffusal length of the holes. Ln is called diffusal length of the electron. Na is the acceptor concentration, Nd is the donor concentration. Dp is called the diffusion constant or diffusion coefficient. Dn is called diffusion constant or diffusion coefficient. A is the area, right? Q is the charge of electron, 1.6 into 10 raised to power minus 90, and Ni is nothing but intrinsic carrier concentration. So sorry, write it in what is small? Ni square, intrinsic carrier concentration. So when the diode is reverse biased, two topics are important. First of all, how to find the transition capacitance and what is the effect, right? And second one is what? Question based on reverse saturation current normally, right? So this type of two questions. So I think now you are ready to solve some questions, everyone. So just quick revision, already I have given you the formula. So this is the PN junction, right? Here always watch the diagram carefully. It is P side is given, N side is given, and that's why here we are getting the positive and negative ion. Applied electric field will be in this direction. Induced electric field will be in same direction. So battery induced electric field, built-in electric field, they both are in the same direction when the diode is reverse bias. Already in this diagram, again it is visible, applied electric field in the same direction. Built-in electric field, again it is in the same direction. Okay, then this is about the capacitance. This is about the reverse bias IV characteristics when the diode is forward bias. This is the reverse saturation current. In second case, that is the reverse saturation current from this point to this point. Everyone tell me if it is the I01, this is the I02. So this is the curve number 1, this is the curve number 2. Out of this two, 1 and 2, which one is for germanium? Which one is for germanium? That is the question. For germanium, which belongs to the reverse saturation current, 1 or 2? Option A, curve number 1. Option B, curve number 2. Second question, for silicon, which is the correct answer? Option 1 or option 2? Okay, tell me which answer is correct out of these two. For germanium, which answer is correct? Second one. Yes. So Ravi, Teja, Hemant, Karthik, you are giving the right answer, because for germanium, what is the value of the reverse saturation current? For germanium, the reverse saturation current, it is in the range of what? Microampere. Or for silicon, the reverse saturation current, it is in nanoampere. I mean, for germanium, the current is very greater than for silicon, reverse saturation current for silicon, right? Second thing, it doubles for every 10-degree rise in temperature. It doubles for every 10-degree rise in temperature, or approximately it increases by 7% per degree centigrade. It increases by 7% per degree centigrade, or it doubles for every 10-degree rise in temperature. And that's why when I have to calculate the reverse saturation current at any temperature, then this is given by 2 to the power T1 minus T upon what, 10, where I0 is the value of the reverse saturation current at T temperature. You have to find the T1. So I0 T1 is given by I0 at T 2 to the power T1 minus T by 10. That is the another important formula. This is called reverse saturation current. Now one thing, why for high range of temperature, for example, if I want to increase the range of the temperature, then silicon is preferable. We can use the silicon up to a 200 degrees centigrade. That this is the reason mostly we prefer using the silicon. Yes, that is the reason. Because what is the ideal value? Ideal value of the reverse saturation current, it should be 0. It is not required, right? But practically it should be as low as possible. So in case of silicon it is low, in case of germanium it is high. And again it doubles for every 10-degree rise in temperature. Because of that, we can use germanium up to 100 degrees centigrade. But we can use the silicon up to 200 degrees centigrade. Right? And that is the reason the silicon is preferable over germanium. Okay? Silicon is preferable over germanium. That is so this is important formula. Yes. If you are going to get the formula based question, use this formula. Otherwise, concept based question, then use that concept. Okay. Finally, one application of that transition capacitance. What is the application of the transition capacitance? That is known as what? Varactor diode. When we are changing the voltage Vj, the capacitance will change. Already I have given the CT, transition capacitance, is proportional to what? Vj raised to power minus 1 by 2 CT. No doubt, in a parallel plate capacitor, we can change the value of the capacitance. For example, in a physical capacitor, what is the formula? Epsilon naught A by W, A by D. D is the distance between the plate, A is the area of the plate. Okay, we can change. Suppose we are increasing the distance between the plate, the capacitance will change. Suppose I want to change the area, I will change the area, but it is practically very difficult. How we are going to change the area? My dear, we have to change the plate, then we can increase the area. Second option is what? Distance between the plates. Yes, we can change the distance between the plate, the capacitor will change. But this is called physical phenomena. And because of this physical moment, we are changing the distance, there may be the chance of what? Wear and tear. Right? So we want to change the capacitor by simply changing the value of the voltage. Right? Why we want to change the value of the capacitor? Simply for tuning. Tuning means what? In a resonance circuit, what is the resonance formula? What is the F0? 1 by 2 pi root over LC. Right? We are having the number of channels. And we want to pass particular channel by rejecting all other channels. Selectivity. Right? That this is the communication. Now I want to watch the Star TV. It is tuned at F01. At the same time, just after some time, I want to watch the GTV. This is the Star. This is the DD. Okay. So we have to tune from Star to a G or Star to a DD and so on. Now L is fixed. We can vary the C physically or what? Voltage tuning. So when I am changing the value of voltage, the value of the capacitor will change and the resonance frequency will change from F01 to what? F02 or F01 to what? F03. Right? So that is called tuning, proper tuning. So it is the Varactor diode is used in what? Parametric amplifier. Remember one point. This is for fine tuning it is used, and that is what? Parametric amplifier. Sometimes we are using this Varactor diode with what? With the 555 timer also. With the 555 timer also. So why I am giving this much information about this point, because this time it is MSQ. Multiple select question they will ask. Which points are correct? Last year 14 questions in electronics branch, 14, 1-4 MSQ. To get the idea about the theory, what about the applications? So number of students are simply mug up the formula, right? Okay. If it is formula based question, you will be able to solve the question. But suppose theoretical question, 1, 2, 3, 4, and out of this 4, one will be based on what? Numerical. Then what about the remaining answer? Yes. So that is the symbol for the varactor diode, variable capacitor. Now remember, this is the equivalent circuit of the varactor diode. Because it is reverse bias, the resistance is very, very high, that is in the range of mega ohm. And this is the resistor of what? Lead. When we are connecting the lead, this is called packaging. Lead has some resistance, so this is called series resistance RS. Because this diode is reverse bias, that's why the internal resistance is very, very high. It is in the range of mega ohm, that is the capacitor in parallel with the R, and this is the packaging resistor. What are the typical values? They will provide you the values in numerical, but remember, CT, it is in the range of what? Picofarad. RS only 8.5 ohm, and the RR, it is what? 1 mega ohm when the diode is reverse bias, and that is the equivalent circuit of varactor diode or transition capacitance or depletion capacitance. This is the model. Okay. In special diodes, no doubt they will not mention LED is mentioned here or what laser is mentioned here, but my dear, it is another name of what? Depletion capacitance or transition capacitance, varactor diode or varicap or volta cap, voltage variable capacitor. These are the name. Remember this formula. How we are going to use this. Okay then. Okay guys, now ready to solve some numericals. Okay, then try to solve this numerical. First of all, this one. Yes, please, everyone, give me the answer for this question. Silicon PN junction at a room temperature of 20 degrees centigrade has a reverse saturation current of 10 picoampere. Then, reverse saturation current at 40 degrees centigrade for the same bias is approximately. A very easy question. Formula based. So, the 20 degrees centigrade, the reverse saturation current is given, and you have to find the 40 degrees centigrade. So, what is the formula? I naught at 40 degrees centigrade is given by I naught at 20 degrees centigrade 2 to the power 40 minus 20 divided by 10. You can find at 40 degrees centigrade, what is that 20? 10 picofarad into 2 to the power 20 by 10, that is 2, that will become what? Oh, at this temperature, what is that? 10 picoampere, so it will become 40 picoampere. 40 picoampere. Very easy. Very, very easy question. That is called formula based question. Okay. So, then next question. Yes. Tell me. In a junction, again, very simple theoretical question. Depletion capacitance increases with the increase in the reverse bias. Depletion capacitance decreases with the increase in the reverse bias. Depletion capacitance increases with the increase in the forward bias. Depletion capacitance is much higher than the depletion capacitance when it is forward biased. Tell me, which answer is correct? Depletion capacitance is much higher than the depletion capacitance when it is forward biased. Which answer is correct? Is correct. It is MCQ. Then, yes, please tell me which answer is correct. Now, depletion, when I am talking about the depletion capacitance means what? Transition capacitance is proportional to what? Vj raised to power minus 1 by 2. What is the Vj? V0 plus Vr. Okay, bhai. When I am increasing the, means we can say Ct is equal to proportional to what? 1 by root over V0 plus Vr when it is reverse bias. or Vj is equal to, when it is forward bias, it is written as Vf. Then in that case, Ct will become proportional to 1 by root over V0 minus what? Vf. Built-in potential minus Vf. First case, when I am increasing the Vr, definitely the Ct will reduce. Definitely the Ct, because when I am increasing the Vr, then V0 plus Vr will increase. What is the reason? Root over V0 plus Vr, this quantity will increase, but it is in denominator, and that's why the Ct will reduce. Okay. But what about this formula? When it is forward bias, when I am increasing the Vf, what about the root over V0 minus Vf? Decreases. When this quantity decreases, what about the Ct? Ct increases. Ct what? Increases. So which answer? The depletion capacitance increases with the increase in the reverse bias. Wrong. The depletion capacitance decreases with the increase in the reverse bias. Right. Depletion capacitance increases with the increase in the forward bias. Depletion capacitance increases with the increase in the forward bias. Right or wrong? Right or wrong? Depletion capacitance increases with the depletion capacitance much higher than the depletion capacitance when it is forward bias. Tell me. Increases with the increase in the forward bias. Yes, everyone, tell me. And then finally, the depletion capacitance is much higher than the depletion capacitance when it is a forward bias. Dekhiye, this is wrong. This point is wrong. What about this point? What about this point? Correct. Right. तो मैंने बोला MCQ, तो आपने बोला ठीक है सर ये वाला. आप ये भी तो देखो, रीड करो क्वेश्चन केयरफुली. अगर बेस्ट आंसर निकालना है तो ये है, लेकिन अगर इफ इट इज MSQ then which answers are correct, we can say. So that is the formula, right? So when we are increasing, so what about the curve? Actually the curve is like this. This is the Vj. Vj minus that what? Applied voltage जो भी हम लोग लगा रहे हैं. This is the Vr or Va. If it is forward bias, then it will become positive. If it is a reverse bias, then it will become negative, and so on. What about the curve? This, when the applied voltage is 0, when the applied voltage is forward bias, when the applied voltage is reverse bias. At this point, we are getting the C0. After that, when we are increasing the Vr in reverse direction, the capacitance will decrease. Here the capacitance will increase. Okay. Okay, right? तो ये है इसका आंसर. नेक्स्ट वन. Now, sometimes very simple question they will give. The depletion capacitance ECE of an abruptly PN junction with a constant doping on either side varies with. So already we have discussed what abrupt junction or step junction or uniformly doped P type and N type, right? Right? So when the reverse bias is given, then junction voltage will increase. Yes, junction voltage will increase. Vj means what? V0 plus Vr. Junction voltage will increase. When we are giving the forward bias, it will oppose the V0, and therefore the junction voltage, the drop across that junction will decrease. Okay. No, and after that we are saying that depletion layer will decrease, then the diffusion will start. There will be the diffusion capacitance. There may be the chance. The depletion capacitance Cj of an abruptly PN junction with constant doping on either side varies with the reverse bias as. What is the reverse bias as? This one. If there is a linearly graded junction, then this formula is correct. For linearly graded junction. Linearly graded means this type of doping. Here the P1, here the P2, it is decreases, not abrupt. Abrupt means this type, step grading or abrupt. Then linearly graded, this is correct. For step graded, this is correct. Okay then. Now next one. There may be the chance just for quick revision, similar type of questions. Why I am giving this type? Similar type of question continuously from last 20 years. Similar type of question in capacitor. Tell me what is the answer. The small signal capacitance of an abrupt PA positive N junction is 1 nanofarad at zero bias. If the built-in voltage is 1 volt, the capacitance has the reverse bias of the voltage. Very simple formula. Right. Always use small signal capacitance of abrupt PN junction. What is the new word here? Small signal capacitance. Small signal capacitance means here giving there is a small change in Q because of a small change in what? Voltage. That is called small signal change. Now, is 1 nanofarad at the zero bias. Zero bias means, always remember one formula, CT2 by CT1. Because it is inversely proportional, we can write root over V0 plus VR1 upon what? V0 plus VR2. Since CT is proportional to what? 1 by Vj. That is nothing but 1 by root over V0 plus VR. Use this formula. If the VR is 0, then directly you can use what? V0. Then you can find the value. For example, just one type of question. If the built-in voltage is 1 volt, built-in voltage is given 1 volt, the capacitance at reverse bias of 99 volt is. From this formula, you have to find the CT2. CT1 is given as 1 nanofarad per centimeter square. In first case, only V0 is given. What is the V0? 1 volt is given. VR is 0. In second case, VR is also given 99. Now tell me, this will become 1 by 10. Root of that 100, 1 by 10. So what is the CT2? 1 by 10. 1 by 10 means what? 0.1. 1 by 10 means what? 0.1. Very simple. Formula based question. Right. So this is this type of questions they may ask in exam. Now, here all are formula based. Now, this type of question sometimes. In when the diode is reverse bias, what is the answer for this particular question? Okay. The electric field profile in the depletion region of a PN junction in equilibrium is shown in the figure. Which one of the following statement is not true? Or they may ask which of the following statements are true. So it will become MSQ. Otherwise, it is a MCQ. MCQ. Now, when the diode is reverse bias, then what about the electric field and so on, and what is the diagram here? Now I am going to give you the answer for this question. This is a printing mistake, minus 0.1 micrometer. This is in micrometer. Remember, the electric field profile in the depletion region is given. This is in micrometer. And this is in what? Volt per centimeter. That is the 10 to the power 4. Okay. That is the value it is given. Now, electric field profile in the depletion region of PN junction in equilibrium is shown in the figure. Which one is not true? Now, first of all, normally we have idea about this PN junction. This PN junction. For example, let this is the PN junction. This is the case. What about the standard derivation? In standard derivation, we are saying that let Na is very, very greater than Nd. What about the Wp is very, very less than Wn? Why? Because Na into Wp is equal to what? Nd into Wn. That is very important derivation. Now, very simple. Here, always remember one thing. What about the depletion layer? This is the depletion layer on P side, and that is the depletion layer on N side. Right? Here we are having the negative charge. Here we are having the positive charge, positive ions. Since there is a uniform doping, so we are representing like this. This is the negative charge, very high doping, and this is called positive charge. Remember, this is the Na, and this width is what? Wn, Wp. This is Nd, and this width is what? Wn. And when we are multiplying, this should be equal to that. This should be equal to this area. This should be equal. We are multiplying. And when we are giving the electric field, what about the direction of the, when we are using the Poisson's equations and when we are integrating it, we are getting the electric field like this. Electric field like this. Because it is a neutral area, in this region the electric field is 0. In this region the electric field is 0 because it is a neutral area. Always remember, hole will neutralize the ions. Here the electron will neutralize the negative ions, positive ions. Okay. Now, when I am integrating by using the Poisson's equations, we are getting this type of line. And at this point, because the integration of the square is what? Triangular pulse, we are getting the triangular pulse. And that is the case. So at this point, we are getting the maximum electric field. The maximum electric field occurs exactly at the junction, P positive and junction. This is the junction. This is the junction, and that is what about the electric field. Remember, the electric field is given by what? Minus dV by dx. Electric field is given by minus dV by dx. Okay. Second thing, what is the Poisson's equation? D square V by dx square is equal to minus rho by epsilon s. What is the rho? Volume charge density. Volume charge density. When we are integrating it and when we are applying the boundary conditions, then we are getting this type of diagram. I am not having enough time to derive all these things, but standard one. But this side it is a p type and this side it is what? N type. It is p type, it is n type. N is very greater than nd, and that is a standard diagram. Again, when we are integrating, we are getting the potential barrier here. Again, when I am integrating it, you are going to get the potential barrier here like this. From this point it will increase and here it will become constant, and that is called Vj. Already we have given I have given you the formula for the Vj, and that is the x is equal to 0. This is the minus Wp, and exactly at this point Wn we are getting the Vj. So already I have given you the formula for Vj. So that is called derivation. Vj, junction potential. This is the doping profile, and this is what? Electric field. So exactly at junction we are going to get the maximum electric field. Okay. Then my dear friends, now what is given in the question? It is just opposite diagram. It is given the positive value. If it is given the positive value, then according to that diagram, according to this diagram, first of all, here it is ND type, matlab means N type. Here we are giving ND, here we are giving NA. This will become positive, this will become negative. Right. Now, this is given. Electric field is given, means here, this is the doping, here this is the negative doping. Positive and here negative charge. When I am integrating it, first of all, it will increase. That is the case. Okay, electric field, and that is the ND positive ions, and this is the negative ions. Again we are using the equations. Which answer? Now my dear friends, the left side of the junction is N type and the right side is P type. Yes, left side is N side, this is N type material, and this is P type material. For opposite, that will be the case. That will be the case. Second answer, both the N type and P type depletion region are uniformly doped. Yes, that is correct. Uniformly doped means, again I have given which answer is correct, which is wrong here. So when I am saying that it is uniformly doped means what? In this region the doping is uniform, in that region is doping is uniform. There is a sudden fall, my dear friend. That's why I am getting the square curve. That's why I'm getting the square here, square, rectangular here, and what is the integration of the rectangular? Triangular. So it means what? It is a uniform doping. Suddenly, what is the meaning of the uniform doping? What is the doping in this region? Number of students confused with this point. Yes, it is uniformly doped. In this region, what is the concentration of electron? Nd is very large, suddenly it will fall. Similarly, what is the concentration of hole here? The concentration of hole is very small and suddenly it will increase, and here it is uniform. This is the concentration of hole and this is the concentration of electron. This is N type, this is P type. This is nothing but Nd. This is nothing but Ni square by Na. This is Na. And this is Ni square by Nd. I think now it is clear to you. Uniform doping. Right? Yes. Na is very high, means Vp, Wp is less. But here, so this is the point. This is right. This is right. Both are N type and uniformly doped. Up, try to understand. What is this point? If the P type region, last point, if the P type region has doping concentration 10 to the power 15, then the doping concentration in the N type region will be 10 to the power 16. Yes, my dear friends, try to understand this point. What is the depletion layer in this region is given 0.1. What is the depletion region? It is given 1. So this was the diagram. This is nothing but depletion region in N side. So this is the Wn. And this is what Wp. So Na into Wn, Na into Wp is equal to what? Nd into Wn. So what is the Na is given in last statement? Doping concentration is 10 to the power 15. And what is the Wp? 1. Wp is 1 micrometer. Yes. What is the Nd? 10 to the power 16 into 0.12. We are getting the same result. Yes, this equality is satisfied. The inequality is satisfied, and this is the right one. This is also the right answer. But what about this answer? The potential difference across the depletion region is 700 millivolt. Now, my dear friend, if the electric field is known, how we can find the potential? By integrating it. By integrating. To integrate. So what is the integration of the triangular? To directly find the area of this curve. So what is the area of any triangular wave? Half of base into height. Area. Why I am calculating the area? Because the voltage is given by integration of EDX. Negative. When I want to find the magnitude only, then the area. What is the area? Half of base into height. So what is the base here? 1.1 micrometer. 1.1 into 10 raised to power minus 4, convert it into centimeter, into height 10 to the power 4. Centimeter cancel, and now you can calculate the value. 1.1 divided by, it is the 0.55 into what? 10 to the power 4, 10 to the power 4 cancel out, volt, or we can say 550 millivolt. 550 millivolt. But which answer? This is wrong. So what is asked? Which one of the following statement is not true? Which one is not true, Chinmay? C is not true. So answer for this question is C. If it is asked MSQ, which answers are correct, then we can say ABD is the correct one. ABD is the correct one. So all new students, please get the command over this diagram. This is a very, very important one. Now, this is the very, very important one. Now, this is about the transition capacitance. Now, when the diode is forward bias, what will happen? When the diode is just forward bias, then remember what is the formula for the forward bias junction, right? 0.55 millivolt. When the diode is forward bias, P side is connected to positive terminal, N side is connected to negative terminal. Then what about the field? Remember, built-in electric field and the applied electric field will oppose each other, right? Oppose each other. And that is the diagram, and that's why the potential, that's why the depletion layer will decrease. Depletion layer will decrease. Now, what is the formula for the current? That is a standard formula for the current. I is given by I naught e raised to power V by eta Vt minus 1. Now, as you know, eta is 1 for germanium, eta is 2 for silicon for low current, but sometimes in a particular numerical, if it is high current is given, remember always eta is 1 for germanium as well as silicon. Where temperature, it is in degree Kelvin, right? Here it is here. Normally we are using this. V is the voltage across the diode. Vt already you know, kT by Q. Vt, as you know, volt equivalent of temperature, and eta is called ideality factor. Normally we are calculating this value, temperature in degree Kelvin, but directly we have the idea about the Vt, to directly you can use. But remember, if the in a forward bias, if this voltage is high, that is given in volt something, then directly you can neglect this one, and I is nearly equal to I naught e raised to power V by eta Vt. Right, E by eta Vt when the applied voltage is greater than eta Vt. So check this, then you can neglect one here. You can neglect one, and that is called, normally when we are finding the ratio, this is a very, very important formula. This will become very important formula. So that is the reverse saturation current. Now, solve some questions. First of all, what is the question here? First question, a silicon PN junction is forward biased with a constant current at room temperature. When the temperature is increased by 10 degrees centigrade, the forward bias voltage across the PN junction. Right. What about the voltage across the diode? First of all, let this diode is forward bias. This voltage is V. But when we are increasing the temperature, the voltage across the diode will what? Reduce. Voltage across the diode is reduced when it is forward bias. So what is the change? The temperature coefficient with respect to temperature, it is given by what? Minus 2.5 millivolt per degree centigrade in some books. In some books, it is given minus 2.5 millivolt per degree centigrade. For example, in Millman Halkias. In Cedra and Smith, it is given as minus 2 millivolt per degree centigrade. That is the value. When temperature increases by 1 degree, it is decreased by 2 millivolt or 2.5 millivolt. So what is given? A silicon PN junction is forward biased with a constant current at room temperature. When the temperature is increased by 10 degrees centigrade, the forward bias voltage across the PN junction, it will increase wrong, it will increase wrong, it will decrease by, so this 2 millivolt or 2.5 millivolt multiplied with the 10, then which answer is correct? D. So 2.5 into 10, you will get the answer 25 millivolt per degree centigrade. 25 millivolt per degree centigrade. Again, formula based question, right? That is the property. On the basis of same, they will ask another type of different types of questions. Then second important theory on the forward bias is what? Diffusion capacitance, right guys? So very, very important topic. Remember, I am giving you the formula. They will ask formula based question on diffusion capacitance. When the junction is forward bias, what is the formula for the diffusion capacitance? It is an incremental capacitance defined as the rate of change of injected charge with voltage called the diffusion or storage capacitance. What is the meaning of this? Very simple. When we are making the diode forward bias, what will happen? Large number of holes will diffuse from P side to N side, where large number of electrons are present. So when we are making the junction forward bias, remember one thing. First of all, it will reduce the potential barrier. Because of this potential barrier, the hole will diffuse from N side to P side. That is called minority carrier injection. Because the status of hole is minority, this process is called minority carrier injection. Minority carrier injection. From higher concentration to what? Lower concentration. Once the electron holes enter into the N side, definitely they will recombine with the electron. So after injection, there will be the recombination. Recombination with the electrons. And finally that is collected and there will be the current And that current is what? Actually, it is a diffusion current when the diode is forward biased. Okay. Then what will happen? When the hole move from P side to N side, so what is the status of hole? Minority carrier in N side. So when we are making more and more forward bias, large number of hole will move from this point to this point, and there is a storage of what? Minority charge carrier in this region. Storage of minority charge carrier because of forward bias. When we are increasing the voltage by del V, there will be the increase in what? Minority charge carrier. And this change in charge because of change in voltage is called diffusion capacitance. Change in charge because of change in voltage is called diffusion capacitance. So what is the change in charge? This is in the case of reverse bias, there is a change in what? Depletion layer. There is a change in depletion layer, we are increasing the acceptor ions and donor ion in depletion layer, right? But here, when we are making the forward junction more forward bias, more hole will move from P side to N side, more electron will move from N side to P side, and that phenomena is called minority charge carrier injection. And there will be storage of minority charge carrier. When we are making more forward bias, more minority charge carrier storage, and that is called diffusion capacitance. Okay, so that is the formula. This is written, it is an incremental capacitance defined as the rate of change of injected charge with voltage, called the diffusion or storage capacitance. Then this is given by dq by dv or dq by dv, and that is the standard formula for diffusion capacitance is tau, that is mean lifetime, and g, where g is called conductance I by eta Vt. Incremental conductance, it is equal to 1 by R, where R is called dynamic resistance. Dynamic resistance. This time try to use this formula. Please remember this formula. This is the diffusion capacitance. They may ask question on this, right? So this is important one. Then second important thing, when the diode is forward bias or reverse bias, theoretical question on PN junction I am going to cover. Second important topic is what? Junction diode switching time. Read this point, junction diode switching time, everyone. Guys, what is the junction diode switching time? Reverse recovery time and forward recovery time. Junction diode switching time means let the diode is forward bias. Suddenly we are making it what? Reverse bias. There is one resistor R. When it is forward bias, there is a large current, and suddenly we are making it reverse bias by using the VR. What about the diode? The current through the diode should be what? 0. Current through the diode should be 0 or reverse saturation current when the diode is reverse bias in this direction. But there are two times, that is called reverse recovery time. Reverse recovery time means what? Storage time plus what? Transition time. Storage time plus what? Transition time. So when we are making the diode reverse bias, from forward bias to what? Reverse bias, suddenly it will not reverse bias. It will take some time. So this time is divided into two parts. One is called storage time, another one is called transition time, TS and TT. And second one, when the diode is already reverse bias and we are making it what? Forward bias. We are making it what? Forward bias. And this time is called forward reverse bias to forward bias. It is called forward recovery time. Forward recovery time. It is negligible. TRR is very, very greater than TFR. In switching time, mainly we are considering what? TRR. Reverse recovery time. Right? Now the reverse recovery time is divided into two parts. One is called what? One is called storage time, another one is called transition time. During storage time, always remember, during storage time, diode almost act as what? Short circuit. Just like a forward bias diode. During storage time, just like a forward bias, it acts as what? Short circuit. But already we are changing the polarity of the applied voltage. That's why the direction of the current will change. But diode normally behaves like what? Short circuit during storage time. and during transition time, the depletion layer will increase, and finally the current in a reverse direction will become I0. That is called reverse saturation current. Reverse saturation current. So I am giving you the diagram. What is the change in the current? What is the change in the current? Let, for example, try to understand this diagram. This is a very, very important diagram. Okay. For example, in this region, the diode is forward bias. Let this is the current. In a forward bias, diode almost acts as short circuit. Let this is the forward bias applied voltage divided by R. R is the resistance. This is the current. Now, when I am making this voltage, just I am going to make it reverse bias at this time. So what will happen? Suddenly the current direction will change because the applied voltage is changed. Now it is connected in reverse direction. But the diode almost acts as what? Short circuit. There will be the current, but it is in opposite direction, and it depends upon the applied voltage. For example, here you are giving the 5 volt, it will become 5 by R, or in a reverse direction you are applying the 10 volt, it will become 10 by R, and it will flow in the reverse direction up to what? During storage time. This is the time at which we are changing the polarity of the battery. After that the current will reduce, and at this point it is become equal to what? Reverse saturation current. That is called transition time. This is called transition time. When it is equal to I0, then we can say now the diode is in reverse direction. So what is the total time from this point to this point? That is called storage. Sorry, that is called reverse recovery time. Reverse recovery time. Okay. So what is now the question on this reverse recovery time? So what is this? This type of questions. This type of questions here. In the circuit shown below, the switch was connected to the position 1. Switch was connected to position 1 at t less than 0. Okay. At t equal to 0, it is changed to position 2. Means when it is connected to 1, it is forward bias. It is written here. It is a forward bias. That is the R. And at t equal to 0, it is changed to position 2. When it is connected to position 2, this switch is connected to position 1. This is the switch. 2 means that diode will become reverse bias. Assume that the diode has 0 voltage drop. The drop across the diode is 0, ideal diode. Storage time is Ts. For 0 to Ts, VR is given by VR. VR means output voltage is given by voltage across the resistor R. Voltage across the resistor R. Which answer is correct? Voltage given by. Now, for storage time, when the diode is forward bias, diode acts as short circuit. The output voltage is exactly replica of the input 5 volt. When I am changing the position of the battery from 1 to 2, the diode is no doubt, it should be reverse bias, but during storage time, it acts as what? Short circuit. Or finally in reverse bias, it should act as what? Open circuit. So what will happen when it is connected? It will act as short circuit. So what is the polarity? Polarity is changed. Plus 5 is converted into what? Minus 5. Plus 5 is converted into minus 5, and that's why the answer is what? A. Plus 5 is converted into minus 5, and that's why the answer is what? A. So that is the case. During TS, diode will act as short circuit, and that is the VR. Already we have changed the polarity, and that's why the VR will become minus 5 volt. Minus 5 volt. Karthik, your answer is correct. Yes, Chinmay, your answer is also correct. That is the storage. So please remember, in EDC for last 5 years, no doubt, there are no questions from this topic, switching time and so on, but we may expect one question on what? This topic, switching time and so on. Then, 1 minute. This is a last very important question. Try to solve this. I'm going to solve this question on PN junction. Then I will give you the idea about the BJT, bipolar junction transistor. For a silicon diode with long P and N region, the acceptor and donor impurity concentrations are 1 into 10 raised to power 17 and 1 into 10 raised to power 15. P region and N region, donor and acceptor doping is given. Na is very greater than Nd. Na is very greater than Nd, 10 to the 100 times higher. The lifetimes of the electron in p region and the holes in the n region are both 100 microsecond. Okay, lifetime means tau n is equal to tau p is equal to 100 microsecond. It is given in the question, right? The electron and hole diffusion coefficient are 49. Electron diffusion current coefficient is 49 and hole diffusion coefficient is 36. Assume the Kt by Q is equal to 26 millivolt. The intrinsic carrier concentration is 1 into 10 raised to power 10 and the Q is equal to this much. And a forward voltage of 208 millivolt is applied. 208 millivolt is applied. What is the weightage mark of EDC? Hemant Krishna. My dear, watch the previous year question paper. Already I think you are available with you. Last year 2022, right? And then get the question from semiconductor physics, get the question from PN junction, get the question from BJT, then get the question from what? MOSFET, CV characteristics. Okay, so sometimes it may be what? 10 to 12 marks. Sometimes it may be from 10 to 12 marks. Sometimes it is 6 to 7 marks. Sometimes it may be more than that, 16 marks. Okay, guys. This is clear. Now tell me. I think sound quality fine, no issue. For a silicon diode with long P and N region, the acceptor and donor impurity concentration are this much. Lifetime is given. Everything is given here. You have to read question carefully. When a forward voltage of 208 millivolt is applied across the diode, the whole current density, only whole current density, it is not as the complete current density, whole current density injected from P region to N region is, whole current density, it is asked. So Karthik Iyer has given the answer 0.514. Okay, we will check. Right. Now try to understand. To solve this question, always remember when the diode is forward biased, what is the formula? I naught e raised to power V by eta Vt minus 1. V is the applied voltage. What is given? We applied voltage 208 millivolt. And what about this is given as a silicon, say for a silicon diode. So when it is a silicon diode, then for silicon ideality factor is what? 2. So what is this one? Vt is 26 millivolt. Right, Vt is 26 millivolt. So what is the 2 Vt? Eta Vt, 2 Vt, 52 millivolt. I am taking because the temperature, Kt by Q, it is given as 26 millivolt. 26 millivolt it is given. Okay, no problem. You will get the 52. So 208 divided by 52 minus 1. That is a very large as compared to what you can compare it. I think this is a very large as compared to that. Then you can neglect one. Now, my dear friends, I naught has 2 parts. In I naught, we are having the 2 parts. First part already I have given you the formula, that is given by AQDP Pn naught upon what? Lp. This is because of holes. And second term is what? AQDN Np naught upon Ln, and that is because of what? Electron. That is because of electron and that is because of holes. And the current only because of holes is required, and that's why focus on this. When I am focusing on this, then what is the current for because of holes only? Then I will become AQDP Pn naught upon Lp e raised to power, this is what? 208 divided by 52 minus 1. Now current density is required, and that's why J will become I by A. Q, dP is given in the question, but Pn naught is not given in the question. It will become Ni square by Nd. into what? LP e raised to power 208 divided by 52 minus 1. You can neglect the 1. Now the Q is given 1.6 into 10 raised to power minus 90. dP is given. What is the dP? It is given 36. Ni square 10 raised to power 10 the whole square. Boss silicon 1 into 10 raised to power 10. This is given in the question. 1.1 into 10 raised to power 10. It is given in the question. Then Nd. What is the doping of the Nd donor ions? 1 into 10 raised to power 5. Donor impurity 1 into 10 raised to power 15. And LP. LP is not given in the question, but tau P is given in the question, both 100 microsecond. So what is the LP? LP is equal to root over dP tau P. dP tau P. So what is the root over dP? What is the dP? Already we have used the dP, that is the 36. Right? We have to use the LP. So dP tau P. 36 centimeter square per volt second. Remember the unit. Centimeter square per second. Well, that is given in 100 microsecond. First of all, convert it into second. 100 into 10 raised to power minus 6 second. From this you will get the LP in terms of what? Centimeter. Now use this LP here in place of this. Put the ND here and then you are going to find the J. You can find now. How many students are able to solve this? How many students are able to solve this? Right? That is what here in analog they will give you what? Reverse saturation current, and then you have to find the formula I naught I. But here, because it is question based on what? Electronic devices in circuit, that's why what is the current because of the holes, what is the current because of the electron, what is the formula for the reverse saturation current, and this much value we have to solve. Use the LP from this point, right, and use here and multiply this e raised to power 208 divided by 52. You are going to get the nearly value. So क्या आ रहा है कार्तिक अय्यर? Check this answer. Your answer is correct. I think I have answer, then I will give you, otherwise no problem. Hmm. 0.5147. Yes. Okay. Put this value, get the answer around 0.51. 0.51 is the answer for this particular question. You can check. Hope so. That is also clear to you. Now this is time to enter into what? BJT. So already we have discussed junction capacitance, depletion capacitance formula, diffusion capacitance formula, formula for the current, formula for the reverse saturation current, how to deal with the PN junction and so on. Now this is for you general aptitude. General aptitude means what? How many marks from general aptitude? 15 marks, right? And it is very easy to get what? 15 marks. To attend a session by Rakesh Talreja sir, that is for GATE 2023. Subscribe our channel so that you will get the notification about this session. Second important session, mathematics, 13 marks, means total 15 plus 13 is what? 28 marks. Now you can secure this 28 marks. Attend this session by Rakesh sir and Ankit Joshi sir. Non-stop maths marathon, complete syllabus in 2 days. That is again coming soon. Subscribe our channel so that you will get the notification. And remember, maths and aptitude is very important subject और आप इसमें पूरे नंबर भी गेन कर सकते हैं. तो this is important session for you. Now the basic structure of BJT. So in a BJT, very simple thing, bipolar junction transistor. Already in analog we have discussed biasing of the BJT. Already we have solved number of questions on BJT. I am going to give you the characteristics and important formula related to what? BJT. Okay, that is the question. अरे session अभी है भाई. Why? The basic structure of BJT means what? This is a emitter region, this is a collector region, and this thin region is called what? Base region. Emitter, collector, and what? Base region. The doping of the emitter is very high. Area of the collector is very high. Right. Second thing, normally we are saying that the doping of emitter is very greater than the doping of collector and just greater than what? Base. So initially this was the correct. NE is very greater than NC, and this is greater than what? NB. But in a recent IC technology we are using NE very greater than NB, or NB is slightly greater than what? NC. This is also correct. Remember that. But always remember the doping of the emitter is highest and area of the collector region is the highest one. That is the case. This is the symbol for what? NPN transistor. This is the NPN transistor. This is the emitter terminal. That is the collector terminal. That is the base current. And that is the symbol for PNP transistor. This is the PN and P transistor. Okay. The NPN and what? PNP transistor. Now there are 4 region, right? Cutoff, active, saturation, and reverse active. So cutoff means both the junction reverse bias, very high internal resistance, and we are using the cutoff region and saturation region for switching action. Means cutoff, as you know, active, that is also called normal active mode or forward active mode. Both the junction for one junction forward bias, this junction is reverse bias. That is for transistor action or for amplifier. Saturation, both the junction forward bias, very low internal resistance. This act as what? Switch on, this act as switch off. Reverse active mode, rarely used configuration, emitter based junction reverse bias, collector based junction forward bias, but we can use this reverse active mode when very low amplification is required. Very low amplification is required, then we can use. Rarely used for low amplification, just like in TTL. TTL we are using this mode, reverse active mode. Okay. Then that is about the current components of the BJT. This is a very important diagram, current components of the BJT. Try to understand this current components. When we are making the emitter junction forward bias and when we are making the collector junction reverse bias, the BJT will be in active region. When the BJT is in active region, large number of hole, try to understand this concept, large number of hole, because it is a PNP transistor, large number of hole will move from base region to what? Emitter region to what? Base region. Some of the hole will recombine with the electron and they will constitute base current, and remaining hole will reach to collector region and they will constitute what? Collector current, that is the IC. Okay. At the same time, some electron will also move from base region to what? Emitter region. When the electron move in this direction, the current will be in opposite direction. So that is the current because of the electron and that is the current because of the hole. But the doping of the emitter is very high, and that's why mainly the current is because of holes in P type. So emitter current is no doubt it is because of hole as well as because of the electron, but mainly it is because of holes. Second thing, some hole will recombine in the N region, they will constitute what? Base current, and remaining hole will reach to collector region and they will constitute collector current. What is the transistor? Transfer of current from low resistance region to what? High resistance region. Transfer of current from this region to that region, that is called transistor action. So my dear, out of these two current, which one is useful? This one, current because of holes. So what about the ratio of these two? We have to calculate. Out of IP, some will recombine. There is definitely the IPC1 is less than what IP. So what is the factor by which it will reduce? We have to calculate. Now next thing, this is what? This junction is reverse bias. When this junction is reverse bias, definitely there will be the reverse saturation current, and that reverse saturation current flows from N side to what? P side. Actually direction is what? N side to P side. That is the direction. N side to P side. Now sometimes they will give you the direction inside, but always remember in P type Direction is what? IC is outside, IB is outside, and IE is what? Inside. In PNP transistor, IE inside, and that's why we are giving this type of symbol, IE inside, IC outside, IB outside. But they may change the orientation. If suppose that is given inside, no problem, that will be the negative value. If IC is given outside, that is the positive value. If it is given inside, that will be the negative value. Okay. Now, there is a current that is called what? Reverse saturation current, and that is the value. So, normally in analog, we are writing the one formula, IC is equal to alpha IE plus what? ICO. Alpha IE plus ICO. Okay, alpha is called large signal current gain for common base. So that is the formula which is valid for active region. On the basis of this, again we are getting the next formula that is called IC is equal to beta IB plus what? 1 plus beta times of ICO. 1 plus beta times of ICO. This formula we are using in case of common base, because, and that's why the alpha is called large signal current gain for common base. Or this formula we are using with the common emitter, where beta is called large signal current gain for common emitter. This is the beta IB. Always remember, IE is equal to what? Sum of the incoming current is equal to outgoing current, and that's why we can write IC plus IB. IC plus IB. So we are using this formula. Okay. Then these are the very important and basic idea about the BJT. Now simply, when we are making this junction forward bias, emitter junction is forward bias, try to understand. What about the potential barrier here? Potential barrier decreases. Watch this diagram. Potential barrier decreases by what value? Minus VEB. No doubt, when there is when we are not applying the voltage, there will be the potential barrier, built-in potential. Already I have given V0. But when we are making the junction forward bias, potential barrier will reduce. When we are making the junction reverse bias, potential barrier will increase. So tell me, they will give you this type of diagram. From this we can watch potential barrier increases. From this we can watch potential barrier. Initially this is the potential barrier. Now it is reduced by VEB. Now this is only the potential barrier, and this is given by V0 minus VEB. And that's why we can say emitter junction is forward bias and collector junction is reverse bias, and transistor is in what? Active region. Right. When the junction is reverse bias, mobile charge carriers will be what? 0. Or when the junction is forward bias, large number of holes and electrons will try to cross the junction. So actually what will happen? When we are making the junction forward bias, try to understand this diagram. This is a very important concept here. When we are making the junction forward bias, this is the minority carrier concentration. This is the minority carrier concentration. The doping of this region is very, very large. That this is the P side, N side. Na is very, very greater than Nd. What is the minority charge carrier? This is called minority charge carrier, Np0. This is called minority charge carrier, Pn0. Okay. When I am making the junction forward bias, large number of hole will diffuse from P side to N side, and that is the characteristics. Large number of electron will diffuse from N side to P side, but the concentration on the N side is low. That is the case. And ultimately it will become equal to what? Minority charge carrier concentration at far from the junction. That is the characteristics when the junction is what? Forward biased. When the junction is reverse bias, then this is the junction, and this junction is reverse bias. Initially, the minority charge carrier concentration is this one. Okay, minority charge carrier concentration. This is the Np0 and this is the Pn0. Here again the ND is less, Na is very large, and that's why the minority carrier concentration is small, because NP naught is equal to Ni square by Na, or Pn naught is equal to what? According to mass action law, Ni square by Nd. Nd is less, and that's why Pn naught is high. But when we are making the junction reverse bias, so exactly at junction, what about the charge carrier? It will become 0. Minority charge carrier will become 0. What is the characteristics? This one. The concentration at the junction will reduce. At this point, the concentration will increase at the junction. Now, far away from the junction, it will reduce. Then we can say this junction is what? Forward bias. Directly we can say this junction is forward bias. From this we can say the junction is what? Reverse bias. Means if the diagram is given, like this, that this is the transistor, this is emitter junction, and this is collector junction. Now watch this diagram carefully. Okay, if it is given like this is the minority carrier concentration of this one, this is the minority carrier concentration of what? Let's try to understand. This is the base region, and that is the minority carrier concentration of collector region. If it is given, from this I can say, since the minority carrier concentration is lowest in E region, this is let PNP, it is lowest in P region, and that's why I can say the doping of the emitter is highest. Second, base has highest minority carrier concentration, and that's why it has the lowest doping concentration. So Ne is very greater than Nc, or Nc is just greater than what? Nb. That is correct one. Because from this diagram we can say this is very high, minority carrier concentration is high, means actual doping concentration is what? Low. So Ne is very high as compared to collector, then collector is higher than as compared to what? Base. So that is the we can say. Second thing, once you have the idea about this diagram, now there are 3 or 4 reasons I am explaining you. First of all, if it is active region, then emitter junction is forward bias, collector junction is reverse bias, you are going to get this type of diagram. Yes. Now, when this is the diagram, we can say this is the forward bias. Since the doping of the emitter is very high, large number of hole will diffuse, but at the collector junction they will become what? 0. Concentration will become 0. This is the collector junction, this is what? Emitter junction. So this junction is forward bias, that junction is reverse bias, and that's why the transistor is in active region. This is called normal active region. Second diagram, if it is given, for example, it is given like this. Yes, right. If it is given like this, we can say this junction, collector junction is forward bias, emitter junction is reverse bias. Tell me in which mode? In which mode? Everyone give me the answer in the comments box. In which mode? This junction is forward bias, this junction is what? Reverse bias. It is because the charge carrier will become 0 at this point. Large number of hole will diffuse from collector region to what? Base region, and this is the emitter region. Yes. Then if this is the case, means this is the reverse bias and that is the forward bias. It is opposite of what? Active. That is called reverse active mode, or right inverse active mode. So reverse active mode or inverse active mode. Then if that is the case, try to understand, this will become 0. This is again at concentration at this point is 0, concentration at this point is 0, means this is reverse bias, this is reverse bias, both are reverse bias. When both the junction, emitter junction is reverse bias, collector junction is reverse bias, we can say it is in what? Cutoff. It is in what? Cutoff. Yes, Ankit Tiwari, your answer is correct. So that is called cutoff. Okay. And in what? In a saturation, what will happen? Both the junctions should be what? Forward bias. To forward bias, this type of diagram you are going to get. Forward bias, this type of diagram you are going to get. To remember always this one. This is the when the junction is forward bias, that is the case, or when the junction is reverse bias. When the junction is what? Reverse bias. And this will give you the idea about what? This will give you the idea about the concentration. If the minority carrier concentration is low, doping concentration is high. Means Na is greater than Nd, and that's why it is smaller. This is larger. So dash line represent what? Minority carrier concentration. So already in GATE that question is given, right? You can solve, we will solve that particular question. Second important thing is what? This one. Second important thing is this formula. Remember this formula. A small signal or sinusoidal common base current gain is defined as alpha. Normally in analog we are saying that alpha, yes sir, IC is equal to alpha IE plus ICU. We are using this formula in active region. But in EDC, what is alpha? What is alpha? Sir, please base on diagram one more time. Matlab base on diagram. Which diagram? 1 minute. This one. This one. Okay, Ankit. How you are deciding? Reverse active. Means whether it is a forward bias or reverse bias, you have confusion. Okay. For example, when I am making the junction forward bias, what will happen? Large number of hole will diffuse from P side to N side. So already, for example, I am having the 100 holes here. Now, when I am making it forward bias, then forward bias means potential barrier will reduce. So large number of holes will diffuse. Let extra 1000 holes will diffuse, but they will recombine with the electron. So extra, what is the concentration of hole at the junction? 100 plus 1000, it will become 1100. It will become what? 1100. Now the 1000 introduced from P side to N side, they will recombine with what? Electron. When they will recombine with the electron, so when they are moving in N region, definitely the concentration will what? Reduce. The concentration will reduce, and they will follow this formula. Pn naught plus excess enter into that. This is the 1000 e raised to power minus x by Lp. They will recombine and they will reduce. Similarly, electron, what is the Np naught plus what? Excess electron concentration introduced, e raised to power minus x by Ln. They will also reduce. Means this is the formula for what? When the junction is forward bias. Extra hole will diffuse from P side to N, extra electron will diffuse from N side to P side. Okay, this is clear. We can say it is a forward bias. When it is reverse bias, what will happen? Depletion layer will increase. When the depletion layer will increase, so what about this layer? Here it is only immobile charge carrier will exist. No mobile charge carrier exists. So what about the minority charge carrier? The minority charge carrier, here it is electron. And what is the majority charge carrier? Only we are saying about the minority charge carrier. So here it is an electron, here it is a hole. At the far away from the junction, what is the minority charge carrier? Ni square by Na. At the junction, it will reduce to 0. Far away from the junction, it is Pn naught. At the junction, it will reduce to what? 0. And that's why we can say this junction is what? Reverse bias. So this is simple diode, P type, N type. This is reverse bias, that is forward bias. Now in a BJT, we are having the two junction, emitter junction and what? Collector junction. So directly we can say, if that is the case, extra hole will enter from or injected from P type to N side, this junction is forward bias. Extra, well, that is the deficiency of the holes. It will reduce to 0 at this point. That's why we can say it is a reverse bias. This is forward bias, this is reverse bias. Okay. Now, this is forward bias because the extra holes will diffuse from C side toward collector toward base. That's why this is forward bias. Excess hole. And what about this? At this point, it will become 0. Dash line represent actual concentration. But this is now reduced. So that's why it is called reverse bias, that is called forward bias, reverse active mode. In that case, at this end both become 0, and that's why it is called both the junctions is what? Reverse bias. Now I think this is clear. Ankit, now it is clear. Or if suppose it is given like this type of diagram, here it is reducing, this type of diagram, here it is, they will make a diagram like this. For example, the concentration increases from this point to this point, that point to that point, means both the junction will be what? Forward biased. Okay. Okay then. Now, so my dear friends, this is the formula for the alpha. There are, always remember, when I am talking about the region means simply now this is the emitter current. I am talking about the NPN transistor. Large number of electron will move from N side to P side, and they will constitute a current in opposite direction. Okay, no problem. So there will be the two emitter current. In NPN transistor, direction of emitter current is outside. There will be the two emitter current. One is called INE because of electron, and another one is called IPE. That is because of holes. So INE is very greater than IPE because the concentration of emitter is very greater than concentration of holes in base region. That's why. So we are getting the ratio of JNE upon JNE plus JP. That is called emitter injection efficiency. Second one, now it will move further away. So we are representing in terms of what? Current density. You can put by divided by A, it will become current density, divided by A, it will become current density, and they will constitute emitter current IE. Okay. Now, when the electron will move, some will recombine and they will constitute what? Base current, and some will reach here and they will constitute what? Collector current, and that is called alpha INE. Here alpha INE is called alpha T, that is called ICE. INC means, for example, 1000 hole will enter here. Out of 1000, 100 will recombine. So 900 will reach to what? Collector area, and they will constitute collector current. Why I am giving the opposite direction? Because electron is moving from emitter to collector. But what about the current? Current will be in opposite direction. And finally they will constitute a collector current. IC. Okay. Now, at the same time, in this region, there will be the generation as well as what? Recombination will occur. When there is in this region, there is some recombination will occur, right? Generation, and because of generation and recombination, there will be one current, that is called JR. So what is the total current here? Because of electron, because of hole, and because of new hole electron pair generated in this region, that is called emitter depletion area. Depletion area in emitter junction. But it will contribute in IE, but it will not contribute in what? IC. And there will be a transfer of current from emitter junction to what? Collector junction. So when we are considering all these things, what is the overall alpha will become? So this alpha is called alpha. Overall alpha will become, this is called emitter injection efficiency. This is not the base transport factor. Emitter injection efficiency. This is called base transport factor. Base transport factor, and this is called emitter injection efficiency. So please correct it, no problem. This is the emitter injection efficiency. So alpha is equal to, overall alpha is equal to emitter injection efficiency alpha T into what? Recombination factor. Recombination factor. So this formula, it is very important, my dear. Directly they will give you the formula based question. So please revise this formula. In exam hall, you have to solve the direct question on this formula. They will give you the value of the emitter injection efficiency, transport factor, and recombination factor. Multiply it, you will get the overall alpha. That is a question in EDC. That is a question in EDC. Now, Next important theory. I'm explaining you the theory. So first on the BJT, what about the curve, whether it is a forward bias, reverse bias. Second, emitter injection efficiency, transport factor, recombination factor, overall alpha. Third thing is what? Early effect. That is given by the JM early. That's why it is called early effect, or it is called base width modulation. Base width modulation. So what are the consequences of the base width modulation? Everyone tell me, what are the consequences of the base width modulation? Base width modulation means, very simple, when we are increasing the voltage in reverse direction, like this is the PNP type, we are making this junction forward bias, we are making this junction reverse bias, right? When we are increasing the voltage in reverse direction, then depletion layer increases. When depletion layer increases, the effective base width decreases. This is called effective base width. The physical base width is WB. When we are making the depletion layer reverse bias, this collector junction reverse bias, depletion layer will increases in N region, and because of that, effective base width decreases. So what is the effective base width? Effective base width means the width where recombination occur, okay. Now try to understand. Initially, let 1000 hole will enter. This junction is forward bias. Try to understand this concept. This complete base width is available here. Initially, I am making it forward bias, so 1000 hole will enter here. For example, just I am giving you the number 1000. Large number of electrons are present. That's why this hole will recombine with the electrons and they will constitute a base current. If suppose 100 hole will recombine with the 100 electron, then definitely 100 will constitute a base current and remaining 900 will constitute what? Collector current. 900 will constitute collector current. Okay. This will collector current. Now, try to understand, if suppose I am decreasing the base width, then definitely the recombination will decrease. If suppose I am reducing the base width, the recombination will reduce. When recombination will reduce, out of 1000, 50 will recombine and 950 will reach up to what? Collector region. So base width, if suppose I am reducing the base width, recombination reduces. Recombination reduces means more, 50 will recombine and 950 will reach to what? Collector area. This 50 will constitute base current and 950 will constitute what? Collector current IC. What is the meaning? Collector current increases, base current decreases. So collector current increases, base current decreases, and base current is called recombination current. That is the logic. So when I am making the junction reverse bias, depletion layer increases. Because of depletion layer increases, effective base width where recombination occur decreases, because now we have electron only in this region, right? So recombination decreases, and because of that decrease in recombination, base current reduces but collector current increases. Collector current increases. Always remember. So what is the consequence of the early effect? So there are three major consequences of the early effect. First one, when we are making the VCB increases, collector junction reverse bias, more reverse bias, collector junction more reverse bias, recombination decreases, and therefore alpha increases, IC increases, and but remember one thing, IB decreases, base current decreases. Second important, emitter current. Second, emitter concentration gradient increases. Now revise this point, we have limited time. So dPy, concentration gradient increases, and that's why the emitter current also increases, because it is a diffusion current. It is a diffusion current. A third important is what? Punch through. Punch through means when we are increasing the VCB more and more, collector junction will become more reverse bias, depletion layer increases, and ultimately depletion layer width will become physical width. And what is the effective base width? Will become 0. When this occurs, this is called punch through or reach through. Means complete base region is covered by what? Depletion layer. And that phenomena is called punch through or reach through. Transistor action ceases. Now it will not work. That is called one type of breakdown. That is punch through or reach through. So that is the extreme of what? Early effect or base width modulation. Direct question on that. Yes, base current. Definitely Chinmay, your answer is correct. I think now it is clear. This is clear to you everyone. This is a very important point. 3 effect of early or base width modulation. Direct question on this. Then tell me, already I have given you idea about that. What about this? Watch the diagram and directly you can say in which mode. This is the emitter junction, this is the collector junction. No need to read the question, directly you can say if it is the excess minority carrier enter into this junction is forward bias. This junction is what? Reverse bias. When this junction is forward bias means collector junction is forward bias, emitter junction is reverse bias because it is given collector here, base here, emitter here. This junction is forward bias, that junction is reverse bias means it is in which mode? Inverse active mode. Inverse active mode. This is the only of 1 marks question. Yes, 1 mark question. Option C, inverse active mode. This type of question in GATE exam, theoretical question. Okay. Now I am going to explain you the characteristics of the 3 configuration. We have the 3 configuration. What are the configuration, my dear students? One configuration is common base, another configuration is common collector, third most important one is common emitter configuration. But in EDC, they may ask question from common base, common emitter or common collector. So remember one thing, common base means what? When the base terminal is common to input and output, we are giving input to the emitter, output to the collector. Input to the emitter, output to the collector, then this is called common base configuration. Common base configuration. Then one thing, this table, revise this table. For example, there are 3 properties, AI, AV, and third one is what? AP, power gain. That is nothing but AI into AV. Right? Let this is 1, this is 9. We are increasing the current, then voltage gain will decrease. 8, 3, 7, 4, 6, 5, 5, 6, 4, right? And then 7, 3, 8, 2, 9, 1. So that will be the case. Current gain increases, voltage gain decreases. What about the product? 9, 16, 21, 24, 25, 24, 21, 16 and 9. So at this point we are getting the maximum power gain. But AI and AV are moderate and this is called common emitter configuration. When 9 into 1, that is the current gain is lowest but voltage gain is highest. So this is the common base configuration. Just I am giving you an example. When the current gain is highest but voltage gain is lowest, this is the characteristics of what? Common collector. This is the common collector. So we are having the 3 different types of configuration. If you want highest power gain, then common emitter configuration. If you want highest voltage gain, then common base configuration. And if you want highest current gain, then it is a common collector configuration. These are the characteristics of, right, common emitter, common base and common collector. Why we are using different types of configuration, right? Then I'm in a quick revision, I'm giving you the properties and important points related to common base. This is a very important one. Now, what about the properties of the common base configuration? First, input resistance is lowest out of these 3 configuration, lowest. Output resistance is highest. Lowest current gain, already I have given you the table. Highest voltage gain, moderate power gain. phase shift is 0. If we are giving the positive, we are going to get the positive value. For negative, we are going to get the negative value. Common base amplifier will offer largest bandwidth and it is more suitable for high frequency application. When I am talking about the bandwidth, in analog we are calculating gain bandwidth product. So current gain bandwidth product. So current gain is the lowest and that's why the bandwidth is highest for this configuration. Bandwidth is highest for this configuration. Remember this property. So this is from the analog. And second one, what are the application? Because the IC is equal to what? Alpha I. The output current is controlled by the input current I, and alpha is almost constant with respect to what? VCB, and that's what is called constant current source. The constant current source. We are using as a constant current source. As a non-inverting voltage amplifier, because voltage gain is very high, phase shift is 0. As a high frequency amplifier, because the bandwidth is very, very high, and as an impedance matching device between low resistance to high resistance. Its input resistance is low and output resistance is high. When we want to match the low resistance and high resistance, we are connecting the common base as a buffer. Remember this formula. Remember this point. Between low resistance and high resistance, it used as impedance matching device. So this is a theoretical point, my dear friends. Revise all these points, right? Then second one is what? Common collector configuration. This is the common collector. Common collector means we are getting the output from which region? Emitter region. We are giving input to base, right? We are getting the output from emitter and we are getting giving input to base. So which terminal is common? Common collector is common. Collector is common. So already I have given, it has the lowest voltage gain, that is 1, and that's why it is called emitter follower. Output will follow the input and that's why it is called voltage follower. Current gain is highest. Current gain is highest. Then तो देखिए प्रॉपर्टीज क्या है? Properties: highest input resistance, larger input resistance is mainly due to the feedback resistance Re. Here we are calculating this Ri is equal to what? Hi plus 1 plus HFE Re, that is the part of what? Analog small signal model. Because of this Re, we are having the highest input resistance, lowest R0. Out of 3 configuration, it has the lowest R0. Phase shift is 0, right? And voltage gain is nearly equal to 1. And my dear, common emitter here, we are not mentioning the values. Why? Because common emitter is the most popularly used configuration. So all properties means it has highest power gain, right? Widely used configuration. No doubt it has moderate power voltage gain, moderate current gain, moderate input resistance, moderate output resistance. Everything is moderate. But one thing is highest, that is what? Power gain. Okay, and main purpose of amplification is what? Increase the power. The output of power should be greater than what? Power of the input signal. Output power should be greater than input power. So that is the main purpose of amplification. Last point, breakdown in BJTs. My dear, I am discussing what part of EDC, electronic devices and circuit, not analog. In analog, we are solving numericals, whether it is in cutoff region, active region or saturation region, what is the mode of operation and so on, biasing and stabilization. But here we are discussing what? Topics related to electronic devices and circuit only. So they will ask, what about the breakdown voltages? So there are 2 types of main important breakdowns. One is called punch through and another one is called avalanche breakdown. Punch through already I have discussed. Extreme case of what? Extreme case of early effect. Extreme case of early effect is called punch through or breeze through. Now second one is what? Avalanche breakdown. Now in avalanche breakdown there are 2 junctions. Remember, there are 2 junctions. Watch this. First of all, this collector junction we are making reverse bias and emitter junction forward bias. Now we are calculating this voltage. We are making, for example, it is a PNP transistor. For example, it is a PNP transistor. We are making it reverse bias by applying the voltage at this point. Right? This voltage, this is the PNP or NPN, you can choose. Here we are applying the voltage VCBO. The polarity of this voltage in this direction, so that this junction is reverse bias. Now we are increasing the voltage. We are increasing the voltage, right? And after some time, because of avalanche mechanism, it will break down. We are just before breakdown, we are calculating what is the maximum voltage we can apply just before the breakdown. And that voltage is called BVCBO. That voltage is called BVCBO. What is the meaning of this BVCBO? Maximum voltage applied across the collector base junction when emitter is open. O for when emitter is open. Emitter is open. Or we are applying the voltage between what? Base and collector. So that junction is reverse bias. Maximum voltage. Just before what? Breakdown. Just before the breakdown. And we are taking the reading of this. Second, we are calculating the breakdown voltage between, for example, it is a PNP transistor. I am taking the PNP or NPN, you can choose. Right? So we have to make it junction reverse bias. So this is the polarity. We are saying that BVCEO means we are applying the voltage between emitter and collector. Emitter and collector. And we are making it reverse bias. And we are taking the reading. Maximum voltage just before the breakdown. That is called voltage, breakdown voltage between collector and emitter when the base is open. This base is open. This base is open. Is it clear? Now, so we are having the two types of breakdown voltage. One is called BVCBO, another one is called BVCEO. Remember one thing, the doping of the emitter is very high as compared to which one? With the, try to understand the concept. Collector is common, collector and collector is common. Here base, here emitter. The doping of the emitter is greater than what doping of the base. When the doping is very, very high, so what about the breakdown voltage? Tell me, high or low? When we are increasing the doping, breakdown voltage will reduces. So it is just a point to remember this. BVCEO is less than what? BVCBO. BVCEO is less than the BVCBO. Ravi Shankar, high output impedance but low impedance. Low kya? But low what? Input impedance. Low input impedance means common base. High output impedance and low input impedance, then it is called common base configuration. Common base configuration. Both are moderate, then it is called common emitter. Okay, Ravi Shankar? Yeah, PDF will be available, right? PDF will be available to you on my Telegram channel. I am sending you the, but here students are not attending the session. Ask them to attend the session, right? In the second part on Tuesday. I am going to take the second part, 4 to 8 p.m. and I will cover what? MOS capacitor. And MN sir will take what? MOSFET and what? Special diodes. Please subscribe this channel, and just I am sending you the link so that PDF will be available to you. 1 minute. And that is my link. Okay then. I think now it is clear. These are the two breakdown voltages, and that is the relation between these two voltages. This is the avalanche breakdown. What is the multiplication factor? And that is the value where n is the empirical constant, usually between 3 to 6. Here actually it is the applied voltage VCB, and the BVCBO is the just breakdown voltage, is the base to collector breakdown voltage with the emitter left open. That is, we can, in this way we can find the multiplication factor. Then that is the value. Try to understand this concept. We are calculating the BVCO, or sometimes it is called BVCB or BCO. That is between collector and base, but the polarity of that voltage, we have to keep this polarity so that the collector junction is reverse bias. And this is called BVCO or ECO. This is the case, and that is called breakdown. Once the breakdown occurs, suddenly the current will increase. Once the breakdown occurs, suddenly the current will increase. This is the diagram for common base, and that is the diagram for common emitter or common collector. We are calculating two values, common emitter output characteristics. This is the common base output characteristics. Okay, and this type of questions they may ask. Now please tell me which answer is correct. Right, the breakdown voltages of a transistor with its base open is BVCO, and that with emitter open is VBCO. Then it is not equal, right? This is not equal. Same. It is, both are related, right? Because the doping of emitter is high, that's why the breakdown voltage is low. Breakdown voltage is low, and that is the answer. The theoretical question, right? 1 mark question, theoretical question. So that is about the BJT, and you want to solve some numericals on the BJT, then attend the session. For what analog? In analog, we have given you the idea about what biasing and stabilization, and number of questions based on what MOSFET, number of questions based on BJT, and so on. So this is all about this session. Already I have covered the PN junction and what BJT. So this is a GATE and ECE test series. Now it is time to join the test series. Get unlimited access to full length mock test, subject test. Link is given in the description box. Okay guys. And what about the test then? 60 plus test covering GATE and ECE. Detailed mock analysis, virtual scientific calculators are available. 4,000 plus practice questions are available. All India open mock tests are available. That is curated by what? GATE experts. मैंने आप लोगों को बताया ना, जो अभी हम लोगों ने क्वेश्चन सॉल्व किया, अभी देखो एक क्विक रिवीजन था 2 घंटे में. 2 घंटे में इतने सारे टॉपिक्स को कवर करना है, नो डाउट. कंप्लीट रिवीजन तो आप ऐसा नहीं बोल सकते कि पॉइंट टू पॉइंट सब कुछ कवर होगा. थैंक यू चेतन, ड्रीमर, थैंक यू वेरी मच, राइट. लेकिन एक बात बताओ, if we are giving these topics are important, suppose already it is a time for what? Revision, quick revision. Suppose you missed some topics, for example breakdown voltage, for example what early effect or punch through or reach through. Definitely through this session we can revise all those important topics. So it is a quick revision. Now try to attend session on what? Tuesday, and tomorrow again we have session from 10 to 2 p.m. So please attend those session. And this is about that. So you are on BYJU'S exam prep. Thank you for attending the session. Thank you very much. And that is for you. Please go through this, and you will get the link for byju'sexamprep.com, and as well as you will get the link for what? Our Telegram channel. Thank you and good night. Password, yes, Hemant Krishna. Transistor is the password.